Thousands of years ago, long before modern cities or written history, a frozen world stretched across much of the Earth. Towering glaciers carved valleys and reshaped entire landscapes, while endless plains of snow and ice became home to powerful creatures. Woolly mammoths roamed in great herds, saber-toothed cats stalked silently through the frost, and giant sloths wandered across frozen forests. Life was harsh, survival uncertain, and every species relied on strength, resilience, and adaptation to endure the relentless cold. Exploring how these creatures lived reveals a story of endurance and transformation during one of the most extreme chapters in Earth's history. It is a tale of survival against ice and time, of species preserved in frozen ground, and of a world far stranger and more dynamic than it first appears. Before we step back into this frozen age, share in the comments where you're watching from and what time it is for you. Then settle in as we uncover the incredible story of life on Earth during the Ice Age. An ice age is a very long period of time when Earth's overall temperature drops a great deal. This leads to large sheets of ice, called glaciers, growing over huge parts of the land, especially near the planet's poles and over high mountains. These ice sheets can be kilometers thick, so heavy that they press down on the land beneath them. When we talk about the Ice Age, most people are thinking of the most recent one, which is formerly known as the Quaternary Glaciation. This long period of cold began about 2,580,000 years ago and is technically still ongoing. Within this large ice age, there have been many colder periods, called glacial periods, when ice sheets grew very large, and warmer periods, called interglacial periods, when the ice sheets shrunk back. We are currently living in one of these warmer interglacial periods, which started around 11,700 years ago. During a glacial period, the world looks very different. Vast areas that are now temperate forests or fertile farmlands would have been covered by immense ice sheets. For example, during the last glacial maximum, which was the coldest part of the most recent major glacial period, about 20,000 years ago, thick ice covered nearly all of Canada, much of the northern United States, large parts of northern Europe, and significant sections of northern Asia. These ice sheets were not static. They slowly flowed like very thick, slow rivers, scraping away rocks and dirt, carving out valleys, and reshaping the land. This movement of ice created many of the landscapes we see today, like the Great Lakes in North America, which were carved out by glaciers and then filled with meltwater. Fjords, which are deep, narrow inlets of the sea with steep sides, were also created by glaciers eroding valleys. The immense amount of water locked up in these continental ice sheets caused global sea levels to drop dramatically. During the last glacial maximum, the sea level was about 120 meters lower than it is today. This fall in sea level exposed vast areas of land that are now underwater. One of the most famous examples of this is the Bering Land Bridge, which connected Asia and North America. This exposed land allowed animals, and eventually early humans, to walk from Asia into what is now Alaska, and then spread across the Americas. Other land bridges appeared, connecting islands to continents or separate landmasses, allowing different species to migrate and mix in ways they cannot today. The shapes of continents changed, and new coastlines were formed, which then disappeared again as the ice melted and sea levels rose. The climate during a glacial period was not just colder, but also much drier in many places. With so much water trapped in ice, less water was available to evaporate and fall as rain or snow in other regions. Stronger winds swept across the dry, unglaciated lands, picking up vast amounts of fine dust. This dust would settle in thick layers, forming deposits known as loess, which can be found in many parts of the world, like China and parts of Europe and North America. These loess deposits often form fertile soils today, showing a lasting impact of the Ice Age on our planet's ground. The world was also a dustier place, with atmospheric conditions quite different from our modern era. The types of plants and animals that could survive in this cold, harsh environment were also very different from what we see today. Large mammals, often called Megafauna, roamed the icy landscapes. These included iconic creatures like the woolly mammoth, with its thick fur and long tusks, and the woolly rhinoceros, both well adapted to the cold. Saber-toothed cats hunted large prey, and giant ground sloths lumbered across the Americas. Many of these large animals are now extinct. and their disappearance at the end of the last glacial period is a topic of great scientific interest. The vegetation was dominated by cold-resistant plants, such as vast grasslands and hardy shrubs, rather than the dense forests we often see in these regions today. Early humans, including Neanderthals and our own ancestors, Homo sapiens, lived and thrived during the Ice Age. They adapted cleverly to the extreme conditions, developing tools for hunting and preparing food, creating warm clothing from animal hides, and seeking shelter in caves or building temporary dwellings. Their survival skills and ingenuity allowed them to spread across the globe, following animal migrations and adapting to diverse, challenging environments. Evidence of their lives comes from archaeological sites, including tools, bones, and stunning cave paintings that depict the animals they hunted and the world they knew. Scientists study ice ages using various forms of evidence. One of the most important sources is ice cores drilled from thick ice sheets in places like Antarctica and Greenland. These cores act like time capsules, preserving layers of ice that formed year after year. By analysing air bubbles trapped in the ice, scientists can learn about the past atmosphere, including the levels of greenhouse gases like carbon dioxide and methane. They can also study dust particles, volcanic ash, and even pollen to understand past climates and environments. Geological features on the land, such as moraines, piles of rock and dirt left by glaciers, and U-shaped valleys, also provide clear evidence of past ice sheet movements. Fossils and bones of ancient animals help us reconstruct the ecosystems that existed. By piecing together all this information, scientists can build a detailed picture of Earth's past climate and how it has changed over millions of years. The understanding of ice ages helps us to appreciate the dynamic nature of Earth's climate. It shows that our planet has gone through many natural cycles of warming and cooling, with profound effects on land, sea, and life. While the most common reference is to the most recent period of widespread glaciation, it is important to remember that Earth has experienced multiple ice ages throughout its deep history, each with its unique characteristics and impacts. The study of these past cold periods is crucial for understanding the Earth system and how it might change in the future. The sheer scale of the ice sheets and the dramatic transformation of the planet during these times truly make the Ice Age a remarkable chapter in Earth's story. The beginning of an ice age is not a sudden event, but rather a long, slow process driven by a complex interplay of factors, with changes in Earth's orbit around the Sun playing a crucial role. These orbital changes are known as Milankovitch cycles, named after the Serbian scientist Milutin Milankovic, who first precisely calculated their effects on Earth's climate. There are three main types of these cycles, and when they combine in specific ways, they can reduce the amount of sunlight reaching certain parts of the Earth, particularly the high northern latitudes during summer, which is key for ice sheet growth. The first of these cycles is eccentricity, which describes the shape of Earth's path as it travels around the Sun. This path is not always a perfect circle. It stretches and shrinks, becoming more elliptical or more circular over a period of about 100,000 years. When Earth's orbit is more elliptical, the distance between the Earth and the Sun varies more throughout the year. This means there are times when Earth is much closer to the Sun, called perihelion, and times when it is much farther away, called aphelion. While the total amount of sunlight received by Earth over a year does not change much due to eccentricity alone, it does affect the intensity of sunlight during different seasons. If Earth's orbit is more stretched out, and the northern hemisphere's summer occurs when Earth is farther from the Sun, then those summers will be cooler, which is a key ingredient for ice to grow. The second cycle is obliquity, or the tilt of Earth's axis. Earth does not spin perfectly upright. It is tilted at an angle. This tilt is what causes our seasons. The angle of this tilt changes over a cycle of about 41,000 years, swinging between approximately 22.1 degrees and 24.5 degrees relative to its orbit. When the tilt is greater, seasons become more extreme. Summers are hotter and winters are colder. When the tilt is less, seasons are milder. Summers are cooler and winters are less harsh. For an ice age to begin, cooler summers are particularly important in the northern hemisphere. If summer temperatures in the northern high latitudes are not warm enough to melt all the snow that fell during the previous winter, that snow will build up year after year, eventually compacting into ice and forming glaciers. So, a period of less tilt often helps usher in glacial periods. The third cycle is precession, which refers to the wobble of Earth's axis, much like a spinning top wobbles as it slows down. This wobble changes the direction of Earth's axis over a cycle of about 23,000 years. Precession affects when Earth is closest to the Sun, perihelion, during its annual orbit. For example, currently, the Northern Hemisphere experiences summer when Earth is near its farthest point from the Sun, aphelion. But due to precession, in about 11,500 years, the Northern Hemisphere will have summer when Earth is closest to the Sun, perihelion. This means that precession can make one hemisphere's seasons more extreme, while making the others milder. For an ice age, if the Northern Hemisphere's summer occurs when Earth is farther from the Sun, and the orbit is also more elliptical, it leads to significantly cooler northern summers, providing prime conditions for snow to accumulate and become ice. The combination of these three Milankovitch cycles, especially when they align to produce less solar radiation in the Northern Hemisphere during summer, is the primary natural trigger for glacial periods within an ice age. However, these orbital changes alone are often not enough to cause a full-blown ice age. Other feedback mechanisms and longer-term geological processes amplify these initial cooling trends. One significant amplifying factor is the concentration of greenhouse gases in the atmosphere, particularly carbon dioxide. During periods when Milankovitch cycles favour cooling, a reduction in atmospheric carbon dioxide can further lower global temperatures. This can happen through natural processes, such as increased absorption of carbon dioxide by colder oceans or changes in the growth of plants. As the planet cools and ice sheets expand, the ocean's ability to dissolve carbon dioxide changes. Also, colder oceans can hold more dissolved carbon dioxide. When carbon dioxide levels drop, the natural greenhouse effect weakens, leading to further cooling and helping ice sheets to grow even more. This creates a powerful positive feedback loop. Cooling leads to less carbon dioxide, which leads to more cooling. Ocean currents also play a crucial role. The distribution of heat across the planet relies heavily on ocean currents, which act like giant conveyor belts, moving warm water from the equator towards the poles and cold water back towards the equator. If these currents change or slow down, perhaps due to the input of large amounts of fresh meltwater from growing glaciers, it can disrupt heat distribution. For example, a slowdown in the Atlantic meridional overturning circulation, which brings warm water to the North Atlantic, could lead to further cooling in the Northern Hemisphere, contributing to ice growth. The albedo effect is another powerful feedback loop. Albedo is a measure of how much sunlight a surface reflects. Dark surfaces like oceans and forests absorb a lot of sunlight, while light surfaces like ice and snow reflect most of it. As glaciers and ice sheets expand, they cover more of the Earth's surface with white reflective ice. This means more sunlight is bounced back into space instead of being absorbed by the Earth, leading to further cooling. This increased cooling causes even more ice to form, creating a powerful cycle that can accelerate the growth of ice sheets once they begin to form. Over much longer timescales, plate tectonics and continental drift also influence the occurrence of ice ages. The position of continents can affect ocean currents and whether large land masses are located near the poles. If continents are positioned over or near the poles, they can provide a stable base for ice sheets to accumulate. For example, the presence of Antarctica over the South Pole and land masses surrounding the Arctic Ocean creates conditions favourable for ice accumulation. Changes in mountain ranges caused by plate collisions can also affect atmospheric circulation patterns and precipitation, influencing regional climates and snow accumulation. These geological changes operate over millions of years, setting the stage for the shorter-term Milankovitch cycles to trigger actual glacial periods. Even volcanic activity can play a part, though often on shorter timescales. Large volcanic eruptions can release vast amounts of ash and sulfur particles high into the atmosphere. These particles can block sunlight, causing a temporary global cooling effect. While a single eruption typically causes only short-term cooling, sustained periods of high volcanic activity might contribute to a cooling trend. Conversely, very long periods of low volcanic activity could allow carbon dioxide levels to build up from other sources, potentially contributing to warming, though the primary driver for ice age starts is usually cooling. When people talk about the ice age, they're usually thinking of a very specific time in Earth's recent past, a time of woolly mammoths and vast ice sheets. However, Earth's history is much longer than that, and our planet has actually experienced many different periods of widespread glaciation, meaning there wasn't just one ice age but several. Scientists often distinguish between a major ice age, which is a long period when the Earth has significant ice at its poles, and perhaps large continental glaciers, and glacial periods within an ice age, which are the colder phases when ice expands, separated by warmer interglacial periods, when the ice shrinks back. We are currently living in an interglacial period within the most recent major ice age. The very earliest known major ice age is the Huronian glaciation, which occurred a very long time ago, between approximately 2,400,000,000 and 2,100,000,000 years ago. This was an incredibly significant period in Earth's early history. It happened when Earth's atmosphere was undergoing a massive change, known as the Great Oxidation Event. Before this, Earth's atmosphere had very little oxygen. But as early life forms like cyanobacteria began to produce oxygen through photosynthesis, oxygen levels rose. This rise in oxygen is thought to have caused a massive decrease in methane, another powerful greenhouse gas that was abundant in the early atmosphere. Without methane to trap heat, the Earth cooled dramatically, leading to widespread glaciation, possibly even covering the entire planet in ice. This was a very different kind of ice age, occurring before complex life forms had evolved. Millions of years later, Earth experienced another set of incredibly severe glaciations during the Cryogenian period, which lasted from about 720 million to 635 million years ago. This period is famous for the snowball Earth hypothesis. Evidence from rocks and geological formations suggests that during at least two major events within the Cryogenian, the Earth may have been almost entirely covered in ice, from pole to pole. The oceans would have been frozen over, perhaps even thousands of meters thick in places. If this snowball Earth scenario is correct, life would have been confined to small pockets where volcanism kept water liquid, or to thin zones of liquid water beneath the ice where light could penetrate. Scientists believe that these extreme ice ages eventually ended due to a massive buildup of carbon dioxide from volcanoes, which slowly warmed the planet enough to melt the global ice sheets. The rapid warming that followed these events might have helped trigger the evolution of more complex multicellular life forms. Following the Cryogenian, the next major period of widespread ice was the Andean-Saharan glaciation, which took place much later, during the late Ordovician and Silurian periods, approximately 450 million to 420 million years ago. At this time, many of Earth's continents were joined together in a supercontinent called Gondwana, which was situated over the South Pole. This geographical arrangement was key to the formation of the large ice sheets. The presence of a large landmass at the pole allowed snow and ice to accumulate without melting. This ice age was not as extreme as the snowball Earth events, but it still had a significant impact on global climate and ocean levels. The growth and decay of these ice sheets influenced the evolution of the early marine life, causing widespread changes in ocean chemistry and sea levels. Then came the Karoo glaciation, spanning a long period from about 360 million to 260 million years ago during the late Paleozoic era. This was another major ice age, and it was influenced by the ongoing formation of the supercontinent Pangaea. As continents moved and collided, they created large land masses over the poles, again providing stable platforms for ice sheets to form. This period was also characterized by significant changes in the carbon cycle, including the burial of vast amounts of plant material that formed the coal deposits we mine today. This removal of carbon dioxide from the atmosphere contributed to the cooling trend. The Karoo glaciation saw large ice sheets covering parts of what are now Africa, South America, Australia, and India, all of which were once connected within Pangaea. Evidence for this glaciation includes distinct scratches on rocks, striations, made by moving glaciers, which are found on continents now far apart but once joined. Finally, there is the Quaternary glaciation, which is the current and most recent ice age. It began about 2,580,000 years ago, and, as mentioned, is still technically ongoing. This is the ice age that most people refer to when they speak generally of the ice age. What makes the Quaternary glaciation unique, apart from its recency, is its distinct pattern of repeated glacial and interglacial cycles. Over the last 2.58 million years, Earth has swung back and forth between colder glacial periods, where ice sheets expanded greatly, and warmer interglacial periods, where they retreated. There have been at least 20 major cycles of ice advance and retreat within this ice age. These cycles are primarily driven by the Milankovitch orbital changes of Earth around the Sun. Within the Quaternary glaciation, the last glacial maximum, LGM, was the peak of the most recent cold period. This occurred about 20,000 years ago, when ice sheets reached their greatest extent. At this time, ice covered large parts of North America, including the Laurentide ice sheet, Europe, including the Scandinavian ice sheet, and Asia. Sea levels were much lower, and vast areas of land were exposed. The climate was colder and drier globally. Following the last glacial maximum, the Earth began to warm up, marking the start of the current interglacial period known as the Holocene epoch, which began about 11,700 years ago. This warming caused the massive ice sheets to melt, leading to significant sea level rise and the reshaping of coastlines. Even within the Holocene, there have been some shorter, colder snaps. One notable example is the Younger Dryas, a rapid return to near-glacial conditions in the North Atlantic region that lasted for about 1,200 years, roughly between 12,900 and 11,700 years ago. This sudden cooling event is believed to have been caused by a disruption of ocean currents, possibly due to a massive influx of fresh water from melting North American ice sheets, which temporarily slowed the flow of warm water to the northern latitudes. The Younger Dryas serves as a reminder that even within interglacial periods, the climate can be highly variable and prone to rapid shifts. Each of these major ice ages in Earth's history had different triggers, occurred at different times, and had varying degrees of global ice coverage. From the early snowball Earth events that drastically reshaped the planet and influenced the evolution of life, to the more recent quaternary cycles that saw the rise of modern humans, these periods of global cold demonstrate the dynamic and complex nature of the Earth's climate system, over millions and even billions of years. Understanding these different types of ice ages helps scientists piece together the long story of our planet's environmental changes. Glaciers and ice sheets are among the most powerful sculptors of Earth's surface, massive bodies of ice that form on land and move under their own immense weight. While often used interchangeably, there is a difference. A glacier is a general term for any large moving mass of ice, typically found in mountainous regions or at high latitudes. An ice sheet, on the other hand, is a much vaster form of glacier, covering an area greater than 50,000 square kilometres, not confined by mountain valleys but spreading out over continents. During the Ice Age, these ice sheets were enormous, covering millions of square kilometres of land that are now free of ice. The formation of a glacier begins with snow. It requires conditions where more snow falls in winter than melts in summer. Over many years, layers of snow pile up. As new snow falls, it presses down on the older layers beneath. This pressure, combined with slight melting and refreezing, causes the snowflakes to change. They first transform into denser, rounded ice grains called firn, which looks like coarse sugar. As more snow accumulates, the weight from above increases, squeezing out the air from the firn. Eventually, after many decades or even centuries of compression, the firn turns into solid, blue glacial ice. This glacial ice is very dense, much denser than fresh snow, and contains only a small percentage of trapped air bubbles. For an ice sheet to form, this process must happen on a continental scale, year after year, for thousands of years. Once enough ice has built up, usually to a thickness of at least 50 meters, it begins to move. Glaciers and ice sheets move in two main ways: internal deformation, also called plastic flow, and basal sliding. Internal deformation occurs within the ice itself. Under the immense pressure of its own weight, glacial ice behaves like a very slow, thick fluid. Individual ice crystals within the glacier deform and slide past each other, allowing the entire mass to flow downslope, even if the slope is very gentle. This movement is continuous, though often imperceptible to the human eye. The ice generally moves fastest near the surface and slowest near the bottom due to friction with the ground. Basal sliding is the second way glaciers move, and it involves the entire body of ice sliding over the bedrock or sediment beneath it. This happens when a thin layer of meltwater forms at the base of the glacier. Even when the air temperature is below freezing, The pressure from the overlying ice can lower the melting point of ice, allowing a film of water to form. This meltwater acts like a lubricant, reducing friction and allowing the glacier to slide more easily. Basal sliding can make a glacier move much faster than it would by internal deformation alone. The presence of this meltwater also allows the glacier to pick up and carry away loose rocks and sediments from its bed. The speed at which glaciers and ice sheets move varies greatly. Most valley glaciers creep along at rates of a few meters per year. However, some glaciers, known as surging glaciers, can experience periods of very rapid movement, sometimes hundreds of meters per day, for short periods. Ice sheets, due to their vast size, tend to move more slowly on average across their main body, but they can have fast-moving sections called ice streams, which are like rivers of ice flowing more quickly through the slower-moving sheet. The speed of ice movement is influenced by factors such as the steepness of the land, the thickness of the ice, the temperature of the ice, and the amount of meltwater at its base. There are different types of glaciers based on their shape and location. Valley glaciers, also known as alpine glaciers, are the most common type of glacier found in mountains. They form in high mountain cirques, which are bowl-shaped hollows, and flow down existing valleys, carving them into distinctive U-shapes. Ice caps are dome-shaped masses of ice that cover mountain highlands or islands, typically less than 50,000 square kilometers in area. They flow outwards in all directions, not confined by topography. The largest type, as mentioned, are ice sheets, such as those that covered North America and Northern Europe during the Ice Age. Today, the only two remaining true continental ice sheets are in Greenland and Antarctica, vast frozen wildernesses covering millions of square kilometers. Some glaciers also extend into the ocean, called tidewater glaciers, where large pieces of ice break off to form icebergs, a process known as calving. As glaciers and ice sheets move, they dramatically reshape the landscape through both erosion and deposition. Erosion by ice is incredibly powerful. One key process is plucking, where meltwater seeps into cracks in the bedrock, freezes, expands, and breaks off pieces of rock. As the glacier moves, it plucks these loosened rock fragments away. Another major erosional process is abrasion, where rocks and sediment embedded in the bottom and sides of the moving ice act like giant sandpaper, grinding and scraping the underlying bedrock. This abrasion creates smooth, polished rock surfaces and long, parallel scratches called striations, which show the direction of ice flow. The erosional power of glaciers creates many distinctive landforms. They transform sharp, V-shaped river valleys into broad, rounded U-shaped valleys. In mountainous areas, glaciers carve out cirques, which are armchair-shaped hollows at the heads of glacial valleys. When two cirques erode back to back, they can form a narrow knife-edge ridge called an arête. Where three or more cirques erode around a central peak, they can create a sharp, pyramid-shaped peak known as a horn, like the Matterhorn. When U-shaped valleys extending to the coast are flooded by rising sea levels, they become deep, steep-sided inlets called fjords, or fjords, common in Norway, Canada, and Alaska. Besides erosion, glaciers are also powerful agents of deposition, carrying and dropping vast amounts of rock and sediment. The material directly deposited by a glacier is called till or glacial drift. Till is typically a chaotic mixture of boulders, gravel, sand, and clay, all unsorted because the ice drops everything it carries without sorting by size. When till is deposited in ridges, these are called moraines. Terminal moraines mark the farthest extent of a glacier's advance, forming a ridge at its snout. Lateral moraines form along the sides of a valley glacier, and medial moraines form when two valley glaciers merge, combining their lateral moraines into a stripe down the middle of the new, larger glacier. A widespread sheet of till left behind as an ice sheet melts is called a ground moraine. Other depositional landforms created by glaciers and their meltwater include drumlins, which are smooth, elongated, teardrop-shaped hills made of till, with their long axes parallel to the direction of ice flow. They often occur in fields of many drumlins. Eskers are long, winding ridges of sand and gravel, formed by meltwater rivers flowing in tunnels beneath the glacier or in channels on its surface. When the ice melts, these riverbeds are left as elevated ridges. Kames are isolated, conical hills of sand and gravel, often formed when sediment collects in depressions on the glacier surface and then drops to the ground as the ice melts. Finally, kettle holes, which often become kettle lakes if filled with water, are depressions formed when large blocks of stagnant ice get buried by sediment and then slowly melt, leaving a pit in the ground. During the Ice Age, these powerful glacial processes were operating on an enormous scale across continents. The Laurentide ice sheet in North America and the Scandinavian ice sheet in Europe were kilometres thick, carving out features like the Great Lakes and leaving behind vast plains of till and loose. The repeated advance and retreat of these massive ice bodies profoundly shaped the landscapes of the Northern Hemisphere, leaving behind a clear geological record of their passage. Even today, the presence of current glaciers and the ongoing rebound of land that was once depressed by ancient ice sheets serve as a constant reminder of the immense power and lasting impact of these frozen giants. The climate during the Ice Age was profoundly different from what we experience today, marked by sustained cold temperatures, different wind patterns, and altered precipitation. While we talk about the Ice Age as a single entity, it was actually a period of many ups and downs, with colder glacial phases and relatively warmer interglacial phases. The last glacial maximum, around 20,000 years ago, represents the coldest part of the most recent glacial period and gives us a clear picture of the extreme conditions. Globally, average temperatures were significantly lower than they are now. Scientists estimate that the average global temperature during the last glacial maximum was about 5 to 10 degrees Celsius cooler than present-day temperatures. This difference might not sound enormous, but it was enough to trigger massive ice sheet growth and transform ecosystems across the planet. In regions near the poles and where the vast ice sheets were forming, the temperatures were much, much colder, sometimes 30 or 40 degrees Celsius below freezing for long stretches of time. The coldest conditions were found directly over the ice sheets themselves, where katabatic winds, dense cold air flowing off the ice, would have made the environment even more severe. The major temperature difference between the vast ice sheets and the warmer unglaciated areas created stronger atmospheric pressure gradients. This led to a world dominated by stronger and more persistent winds. These winds were a defining feature of the Ice Age climate, sweeping across continents with greater force and frequency than today. They played a crucial role in shaping landscapes far beyond the direct reach of the ice. For instance, these powerful winds picked up vast amounts of fine, silty sediment from newly exposed continental shelves and from the broad, braid plain river valleys draining the glaciers. This wind-blown dust was carried for thousands of kilometres and deposited in thick layers called loess, creating fertile plains in places like Central Europe, China, and parts of the American Midwest. The skies would have often been hazy with dust, reducing sunlight and potentially contributing to a cooling effect in some regions. Precipitation patterns were also very different. Overall, the Earth's climate was drier during glacial periods because so much of the planet's water was locked up in the immense continental ice sheets and glaciers. This meant less water was available to evaporate from the oceans and fall as rain or snow elsewhere. However, regions near the margins of the ice sheets received significant amounts of snowfall, which was essential for the growth and maintenance of the glaciers. In other parts of the world, what are now deserts might have received more moisture, leading to the formation of large pluvial lakes and basins that are now dry or contain much smaller water bodies. For example, in the western United States, ancient Lake Bonneville, a much larger ancestor of the Great Salt Lake, existed during the Ice Age, indicating a wetter local climate. Conversely, some areas that are now tropical rainforests may have been much drier, perhaps savanna or fragmented forests, due to shifts in global atmospheric circulation. The seasonal differences were also altered. In the Northern Hemisphere, summers during glacial periods were generally cooler than today. This cooler summer temperature was critical because it meant that not all the snow that fell during the winter would melt away. This allows snow to accumulate year after year, eventually compacting into glacial ice. Winters naturally were extremely long and cold, with vast areas experiencing prolonged freezing temperatures. The duration of daylight hours remained the same, of course, but the intensity of the sun's warmth was significantly reduced in critical areas, allowing ice to persist and grow. The composition of the atmosphere during the Ice Age was also distinct. Ice core records, which preserve ancient air bubbles, show that levels of major greenhouse gases like carbon dioxide and methane were significantly lower during glacial periods compared to interglacial periods. For instance, During the last glacial maximum, carbon dioxide levels were around 180 to 200 parts per million, much lower than the current levels, which are over 400 parts per million. This reduction in greenhouse gases amplified the cooling initiated by Earth's orbital changes, creating a powerful feedback loop that helped sustain the colder climate. The atmosphere also contained higher concentrations of dust, as mentioned, due to the stronger winds sweeping over drier and less vegetated landscapes. Ocean temperatures were colder, particularly in the surface waters of high latitudes. The extent of sea ice was much greater, impacting marine ecosystems and further reflecting sunlight back into space. Ocean currents, which play a vital role in distributing heat around the globe, also changed. The formation of large ice sheets and the lowering of sea levels could have altered the pathways and strength of major currents. For example, changes in the Atlantic meridional overturning circulation, a large system of ocean currents that brings warm water to the North Atlantic, might have contributed to regional climate shifts during the Ice Age, including rapid cooling events. The presence of vast ice sheets themselves influenced regional climates. The sheer mass and height of the ice sheets altered atmospheric pressure systems, creating high-pressure zones over the ice. These high-pressure systems could divert storm tracks and create their own weather patterns. The bright reflective surface of the ice sheets contributed to the albedo effect, reflecting a large percentage of incoming solar radiation back into space, thus helping to maintain the cold temperatures. Another significant feature of the Ice Age climate was the widespread presence of permafrost, permanently frozen ground. This permafrost extended much further south in the northern hemisphere than it does today, covering vast regions of Siberia, Europe and North America that are now temperate. Permafrost affects drainage, as meltwater cannot easily soak into the frozen ground, leading to wetlands and shallow lakes in summer. It also influences vegetation, as only shallow-rooted plants can grow in such conditions. The Ice Age climate was not static. While general trends towards colder, drier conditions prevailed during glacial periods, there were also rapid climate shifts that could occur over just decades. The Younger Dryas event, for example, was a sudden and significant return to near-glacial conditions in the North Atlantic region, about 12,900 years ago, after a period of warming. This shows that the Ice Age climate system could be quite unstable, prone to abrupt changes in response to factors like massive meltwater pulses disrupting ocean circulation. The world during the Ice Age was a landscape transformed, sculpted by the relentless power of ice, wind, and water, bearing little resemblance to many of the places we know today. Vast continental ice sheets covered immense portions of the northern hemisphere, while surrounding areas experienced unique periglacial conditions, and even distant regions felt the effects of colder temperatures and altered sea levels. At the heart of the Ice Age landscape were the continental ice sheets themselves. In North America, the Laurentide ice sheet covered almost all of Canada and extended deep into the northern United States, reaching as far south as present-day Illinois, Indiana, and Ohio. In Europe, the Scandinavian ice sheet covered Scandinavia, the British Isles, and much of northern Germany and Poland. Similar large ice sheets existed in Siberia. These ice sheets were incredibly thick, often reaching 2 to 4 kilometers in places, so heavy that their weight pressed down on the Earth's crust, causing it to sink slowly over thousands of years, a process called isostatic depression. When the ice eventually melted, this depressed land slowly began to rebound, a process known as isostatic rebound, which is still ongoing in some areas today. The surfaces of these ice sheets were vast, relatively flat white plains, interrupted only by occasional high mountain peaks, called nunataks, that poke through the ice. Surrounding the ice sheets were extensive periglacial zones. These were areas not directly covered by ice, but still subject to intensely cold, Arctic-like conditions. A defining feature of these zones was widespread permafrost, ground that remained permanently frozen for at least 2 consecutive years, often extending to great depths. Permafrost meant that water could not drain downwards, leading to a landscape of bogs, shallow lakes, and patterned ground formations, like stone circles and polygons, created by the repeated freezing and thawing of the active surface layer. The vegetation in these periglacial zones was typically tundra and cold steppe, vast treeless plains dominated by hardy grasses, mosses, lichens, and dwarf shrubs. This cold, grassy environment supported immense herds of Ice Age megafauna, such as woolly mammoths, woolly rhinoceroses, and wild horses. Another significant feature of the periglacial landscapes was the prevalence of loess plains. These are vast, flat to gently rolling expanses of fine, yellowish, wind-blown silt. During the Ice Age, strong winds swept across the dry, barren landscapes, including exposed continental shelves and the wide, braided river valleys fed by glacial meltwater. These winds picked up huge amounts of fine sediment and carried it for hundreds or thousands of kilometers before depositing it in thick layers. These loess deposits often buried existing landforms and can be many tens of meters thick. Today, these ancient loess plains form some of the most fertile agricultural lands in the world, a lasting legacy of the Ice Age winds. The immense amount of water locked up in the continental ice sheets led to a dramatic lowering of global sea levels. At the peak of the last glacial maximum, global sea levels were about 120 meters lower than they are today. This exposed vast areas of the continental shelf, land that is now underwater. These exposed shelves often formed broad, low-lying plains, sometimes connecting land masses that are now separated by sea. The most famous example is Beringia, the land bridge that connected Asia and North America across what is now the Bering Strait, allowing animals and early humans to migrate between continents. Other significant land bridges included Sunderland, which connected Southeast Asian islands like Sumatra, Java and Borneo to the mainland, and Doggerland, which connected Great Britain to mainland Europe across the North Sea. These exposed lands created new terrestrial environments and facilitated the dispersal of species. The movements of ice also created and altered many lakes and rivers. As glaciers advanced, they often dammed existing rivers, leading to the formation of huge preglacial lakes at the ice margins. One of the largest was Glacial Lake Agassiz in North America, which was larger than all of the current Great Lakes combined. These lakes often existed for thousands of years before finding new outlets or catastrophically draining. In warmer, drier regions away from the ice sheets, increased rainfall or reduced evaporation led to the formation of large pluvial lakes in basins that are now arid. Lake Bonneville in the western United States, a much larger ancestor of the Great Salt Lake, is a prime example. River courses were also dramatically changed. Some were diverted by advancing ice, others flowed across newly exposed land, and many became much larger and more powerful due to the immense volumes of meltwater draining from the glaciers, forming wide, braided glacial outwash plains, also known as sanders. These plains were vast, flat areas made of sand and gravel deposited by the meltwater streams. In mountainous regions, even those not covered by continental ice sheets, alpine glaciation was far more extensive than it is today. Mountains that now have only small glaciers, or no glaciers at all, were heavily glaciated. These glaciers carved out distinctive U-shaped valleys, straightened former V-shaped river valleys, and created sharp, knife-edge ridges called arêtes, and pyramid-shaped peaks called horns. Bowl-shaped depressions at the heads of glacial valleys known as cirques were common, often holding small, deep lakes called tarns after the ice melted. These mountain landscapes were rugged and dramatic, dominated by bare rock, ice, and thin soils. The vegetation zones across the globe were also shifted towards the equator. Areas that are now temperate forests were often replaced by extensive tundra, steppe, or cold grasslands. Coniferous forests like those found in northern Canada today would have extended much further south in Europe and North America. Even tropical regions were affected. While not experiencing ice, some tropical rainforests might have been reduced to smaller, fragmented patches, replaced by more open savannas or drier woodlands, as global climate patterns shifted. This reshaping of vegetation zones forced animals and humans to adapt or migrate in response to the changing availability of food and habitat. The Ice Age created a world of immense contrasts: colossal ice sheets beside vast windswept plains, newly exposed land bridges connecting continents, and transformed river systems draining enormous temporary lakes. This was a dynamic landscape, constantly changing as ice advanced and retreated, leaving behind a profound and lasting imprint on Earth's surface that we can still observe and study today. The woolly mammoth, Mammuthus primigenius, stands as one of the most iconic and recognizable creatures of the Ice Age, a testament to nature's remarkable ability to adapt to extreme cold. These magnificent proboscideans roamed the vast cold steppes and tundras of Eurasia and North America for hundreds of thousands of years, thriving in environments that would be inhospitable to most modern large mammals. Their physical adaptations were meticulously suited for survival in the frigid conditions of the Pleistocene epoch, a period characterized by widespread glaciation. One of the most striking features of the woolly mammoth was its dense, shaggy coat, a primary defense against the biting cold. This fur was not a single layer, but comprised two distinct types of hair. The outer layer consisted of long, coarse guard hairs, which could reach up to 1 meter in length. These hairs formed a protective barrier, shedding snow and rain similar to a modern yak's coat. Beneath this outer layer was a thick, insulating undercoat of fine, woolly hair. This dense undercoat trapped a layer of air close to the mammoth's body, providing exceptional thermal insulation, preventing heat loss to the frigid environment. The colour of their fur varied, with evidence suggesting shades from dark brown to reddish brown, and even lighter, yellowish tones. This double-layered fur, combined with a thick layer of subcutaneous fat, allowed mammoths to endure temperatures far below freezing, even during the harshest Ice Age winters. Beyond their impressive fur, woolly mammoths possessed other key adaptations for cold climates. Their ears were notably smaller than those of modern elephants, a feature that minimises heat loss from the body's extremities. Similarly, their tails were relatively short. These reduced surface areas helped conserve body heat, a crucial physiological strategy in cold environments. Their skin was also thicker than that of modern elephants, providing an additional layer of insulation. The overall body shape of the woolly mammoth was compact and robust, contributing to a lower surface area to volume ratio, which further aided in heat retention. Perhaps the most distinctive and awe-inspiring feature of the woolly mammoth was its enormous tusks. These were, in fact, elongated incisor teeth, growing continuously throughout the mammoth's life. Unlike the straighter tusks of modern elephants, woolly mammoth tusks typically curved upwards and inwards, sometimes forming a nearly complete circle in older males. The size and curvature varied among individuals and between sexes, with males generally possessing larger and more dramatically curved tusks than females. These tusks could reach lengths of up to 4 meters and weigh over 100 kilograms each. The tusks were not merely for display. They served multiple practical purposes in the mammoth's daily life. They were used for digging through snow to uncover vegetation, a behaviour known as snow ploughing or tusk shoveling. They also likely played a role in social interactions, such as dominance displays among males, and potentially in defence against predators like saber-toothed cats and wolves. The wear patterns observed on fossilised tusks provide direct evidence of their extensive use in foraging and ground disturbance. The diet of the woolly mammoth was primarily herbaceous, meaning they were plant eaters. They were grazers, specialised in consuming the tough, fibrous vegetation of the Ice Age steppe tundra. This environment was characterised by vast expanses of grasses, sedges and other low-growing herbaceous plants, rather than dense forests. Evidence from fossilised stomach contents and analysis of mammoth dung, preserved in permafrost, confirms their diet consisted mainly of grasses, sedges and some flowering plants. They possessed large, flat molar teeth with many ridges, perfectly suited for grinding down abrasive plant material. These molars were replaced several times throughout a mammoth's life, as they wore down from constant chewing. The sheer volume of food required to sustain such large animals meant they spent a significant portion of their day foraging, constantly moving across the landscape in search of new pastures. Woolly mammoths were highly social animals, living in herds much like modern elephants. These herds were likely matriarchal, led by an older, experienced female. The social structure provided protection against predators and facilitated the sharing of knowledge about foraging grounds and migration routes. Herd sizes probably varied, but fossil evidence and comparisons with modern elephants suggest groups ranging from small family units to larger aggregations. Young mammoths would have been protected within the herd, learning essential survival skills from their elders. Males, particularly older ones, may have lived more solitary lives or formed smaller bachelor groups, periodically joining the main herds for breeding. The strong social bonds within mammoth herds would have been crucial for navigating the challenging Ice Age environment, especially during migrations. Mammoths were migratory animals, moving across vast distances in response to seasonal changes in food availability and climate. During warmer months, they would spread out across the northern plains, taking advantage of abundant vegetation. As winter approached, they would move to areas where foraging was still possible, perhaps seeking shelter in more protected valleys or areas with less deep snow. Their migratory patterns likely followed established routes, passed down through generations. This constant movement also helped to shape the landscape as their grazing and trampling created open areas and disturbed soils, influencing plant distribution. The geographical distribution of woolly mammoths was extensive, spanning across northern Eurasia and North America. They were found from Western Europe, across Siberia, and into Alaska and Canada, reaching as far south as the central United States during glacial maximums. This wide range was facilitated by the Bering Land Bridge, which connected Asia and North America during periods of a lower sea level, allowing for easy movement between continents. Their fossils are abundant across these regions, providing a rich record of their existence. Perhaps the most remarkable discoveries are the well-preserved mammoth carcasses found in the permafrost of Siberia and Alaska. These frozen remains, sometimes complete with fur, flesh and even stomach contents, offer an unparalleled glimpse into the biology and ecology of these extinct giants. These discoveries have allowed scientists to study their DNA, diet, and even their parasites, providing insights impossible to gain from bones alone. The woolly mammoth's long reign as a dominant herbivore of the Ice Age eventually came to an end. Most populations disappeared around 10,000 years ago, at the close of the last glacial period, as the Earth warmed and their preferred steppe tundra habitat began to shrink and be replaced by forests. Small, isolated populations survived on islands like Wrangel Island in the Arctic Ocean, until as recently as 4,000 years ago, long after their mainland counterparts had vanished. The exact causes of their extinction are still debated, but a combination of rapid climate change, habitat loss, and hunting pressure from early humans likely played significant roles in their ultimate demise. The woolly mammoth remains a powerful symbol of the Ice Age, a majestic creature perfectly adapted to a world that no longer exists. The saber-toothed cat, most famously represented by Smilodon fatalis, is one of the most iconic and formidable predators of the Ice Age. Despite their common name, these animals were not true cats in the same lineage as modern tigers or lions, but rather belonged to an extinct subfamily of felids known as Machaerodontini. Their defining characteristic and the source of their popular name was the presence of extraordinarily long, dagger-like upper canine teeth, which set them apart from any living feline. These magnificent hunters roamed the Americas during the Pleistocene epoch, specializing in taking down large, thick-skinned prey. The most distinctive anatomical feature of Smilodon fatalis was undoubtedly its pair of elongated upper canine teeth. These teeth could reach lengths of up to 28 centimeters, including the root, and extended well below the lower jaw when the mouth was closed. These impressive canines were serrated along their edges, though the serrations were finer than those found on the teeth of some other extinct predators. To accommodate these massive teeth, Smilodon possessed an exceptionally wide gape, capable of opening its jaws to an angle of about 120 degrees, far wider than any modern cat. This wide gape was crucial for allowing the sabers to be fully deployed in a killing bite, without being obstructed by the lower jaw. Beyond their famous teeth, the skeletal structure of Smilodon indicated a powerful, robust build, quite different from the lithe, agile form of modern big cats. They were heavily muscled, particularly in their forelimbs and neck. Their front legs were remarkably strong, suggesting they were built for grappling and holding onto large, struggling prey. Their hindquarters were comparatively less developed, indicating they were not built for sustained high-speed chases like cheetahs. Instead, their physique points to an ambush predator, relying on brute strength and a powerful pounce to subdue their victims. Their tail was relatively short, similar to a bobcat's, which further supports the idea that they were not pursuit predators requiring a long tail for balance during high-speed turns. The unique dental and skeletal adaptations of Smilodon suggest a specialized hunting strategy. Unlike modern cats that kill by suffocating prey with a bite to the throat or severing the spinal cord, Smilodon sabers were too fragile for a prolonged struggle or for biting into bone. The prevailing theory is that Smilodon used its powerful forelimbs to wrestle large prey to the ground, and then delivered a precise deep stab to the throat or belly, aiming to sever major blood vessels or the windpipe, causing rapid blood loss and shock. The wide gape allowed them to deliver this deep, precise bite without breaking their delicate sabers on bone. This method would have required the prey to be largely immobilized before the killing bite was delivered, highlighting the importance of their powerful forelimbs and possibly a social hunting strategy. The diet of Smilodon fatalis consisted primarily of large herbivores that roamed the Ice Age landscapes of the Americas. Fossil evidence from sites like the La Brea tar pits in California, which contain thousands of Smilodon remains, indicates they preyed upon animals such as ground sloths, young mammoths and mastodons, ancient bison, camels and horses. These were large, often slow-moving animals that would have been challenging to kill without specialized adaptations. The abundance of Smilodon fossils in the tar pits, often alongside the remains of their prey, suggests that these predators were effective hunters within their ecosystem. The social behavior of Smilodon is a topic of ongoing debate among paleontologists. The high number of Smilodon individuals found together in the La Brea tar pits, including many with healed injuries that would have made solitary hunting impossible, suggests that they may have lived in social groups, similar to modern lions. If they lived in groups, they could have cooperated in hunting large prey, caring for injured members, and raising their young. However, other interpretations suggest that the tar pits might have simply acted as predator traps, attracting many individuals independently to feed on trapped herbivores. While definitive proof of social behavior is elusive, the evidence for healed injuries strongly points towards some form of communal living, or at least tolerance among individuals. Smilodon fatalis had a wide geographical distribution across North and South America. Its fossils have been found from Canada down to South America, indicating its adaptability to various environments within the Americas. They preferred open woodlands, grasslands, and savanna-like environments where large herbivores were abundant. They were not typically found in deep forests or extreme Arctic conditions, suggesting a preference for more temperate or subtropical climates, where their ambush hunting style would have been most effective. The La Brea tar pits in Los Angeles, California, represent the richest source of Smilodon fossils, providing an unparalleled window into their lives and the ecosystem they inhabited. These asphalt seeps acted as natural traps, preserving countless animals that became stuck while trying to drink or prey on other trapped animals. The reign of the saber-toothed cats came to an end during the late Pleistocene extinction event, approximately 10,000 years ago, alongside many other large Ice Age mammals. The causes of their extinction are likely multifaceted, involving a combination of factors. Rapid climate change at the end of the last glacial period led to significant habitat shifts, as grasslands and open woodlands were replaced by denser forests in some areas, reducing the availability of their preferred large prey. Additionally, increasing competition with humans, who were also skilled hunters of megafauna, may have played a role. As their primary food sources declined, Smilodon's specialized hunting adaptations, which were so effective for large, slow prey, may have become a disadvantage when faced with smaller, more agile game. Their unique teeth, while powerful for specific kills, were not versatile for general scavenging or hunting, smaller, faster animals ultimately contributing to their demise. The saber-toothed cat remains a captivating symbol of the Ice Age, a powerful and specialized predator that once dominated the ancient American landscapes. Giant ground sloths were among the most colossal and peculiar mammals to roam the Americas during the Ice Age. Unlike their modern, tree-dwelling relatives, these extinct sloths were immense, terrestrial herbivores that could reach sizes comparable to elephants, making them a dominant presence in the ecosystems of the Pleistocene epoch. They represent a remarkable example of convergent evolution, where unrelated species develop similar physical traits in response to similar environmental pressures. The most famous and largest of the giant ground sloths was Megatherium americanum, which lived in South America. This truly enormous creature could stand over 6 meters tall on its hind legs and weigh up to 4 tons, making it one of the largest land mammals of its time, rivaling even a small elephant in mass. Other significant genera included Mylodon and Erematherium, which were also very large but generally somewhat smaller than Megatherium. Erematherium was particularly widespread in North America. These sloths possessed a robust skeletal structure, with thick bones and powerful limbs designed to support their immense weight. Their bodies were covered in coarse, shaggy fur, which would have provided some insulation, though perhaps not as dense as that of the woolly mammoth, as many ground sloth species inhabited warmer climates. A distinguishing feature of giant ground sloths was their massive, powerful claws. Unlike the sharp, retractable claws of cats, these claws were thick, blunt, and non-retractable, more akin to hooves in their constant exposure. They were typically 5 to 10 centimeters long, though on the larger species they could be significantly larger. These formidable claws served multiple purposes. They were primarily used for foraging, allowing the sloths to strip leaves and branches from trees, or to dig for roots and tubers. They also provided a powerful defense mechanism against predators. When threatened, a giant ground sloth could rear up on its hind legs, supported by its strong tail, and deliver devastating blows with its clawed forelimbs. The sheer size and power of these animals, combined with their formidable claws, would have made them a challenging target for even the largest Ice Age predators like saber-toothed cats. The locomotion of giant ground sloths was unique. Due to their large, non-retractable claws, they could not walk flat-footed like most mammals. Instead, they walked on the sides of their feet, a form of locomotion known as knuckle walking for their forelimbs, or walking on the outer edges of their hind feet. This gait would have made them relatively slow-moving, lumbering giants. However, their powerful hind limbs and robust tail allowed them to rear up into a bipedal stance, standing on 2 legs. This posture would have been used for reaching high branches to strip leaves, for digging, or for intimidating predators. The tail acted as a strong tripod, providing stability when standing upright. While slow, their immense size and defensive capabilities meant they had few natural predators once fully grown. Giant ground sloths were primarily herbivores, meaning their diet consisted of plants. Evidence from fossilized stomach contents and coprolites, fossilized dung, indicates they consumed a wide variety of plant material, including leaves, twigs, shrubs, and grasses. Their teeth were large and peg-like, lacking enamel on the chewing surfaces, and were continuously growing. These teeth were well suited for grinding tough plant fibers. Some evidence suggests that certain species might have also consumed small amounts of meat, possibly scavenging on carrion, but this was likely not a primary food source. Their large digestive systems, similar to those of modern ruminants, would have been efficient at breaking down fibrous plant matter. They would have spent a significant portion of their day foraging, slowly moving through the landscape and consuming vast quantities of vegetation to sustain their enormous bodies. The geographical distribution of giant ground sloths was extensive, primarily across North and South America. They originated in South America and migrated north into North America during the Great American Interchange, a period when the Isthmus of Panama formed, allowing animals to move between the 2 continents. Megatherium remained largely confined to South America, while Mylodon and Erematherium successfully colonized North America. Their fossils have been found in a wide range of environments, from grasslands and open woodlands to more arid regions, indicating their adaptability to diverse habitats. They were particularly common in warmer, more temperate regions, though some species extended into colder zones. Fossil discoveries have provided invaluable insights into the lives of giant ground sloths. In addition to bones, well-preserved dung deposits from dry caves in North and South America have offered direct evidence of their diet and the plants that grew in their environments. In some rare instances, mummified remains with preserved fur and skin have been found, particularly in arid regions, providing a more complete picture of their external appearance. These discoveries have allowed scientists to reconstruct their anatomy, understand their locomotion, and analyze their dietary preferences. The giant ground sloths, like many other megafauna, faced extinction at the end of the Pleistocene epoch, approximately 10,000 years ago. The causes of their disappearance are complex and likely involved a combination of factors. Rapid climate change at the close of the last glacial period led to significant shifts in vegetation and habitat. As forests expanded in some areas and grasslands changed, the availability of their preferred food sources may have diminished. Additionally, the arrival and spread of the early human populations across the Americas coincided with the decline of these large animals. Human hunting pressure, targeting these large, slow-moving and relatively defenseless creatures, is considered a significant contributing factor to their extinction. Their slow reproductive rates and specialized diet may have made them particularly vulnerable to these environmental and anthropogenic pressures. The giant ground sloths remain a fascinating example of the unique and diverse megafauna that once roamed the ancient landscapes of the Americas. The cave bear, Ursus spelaeus, was a massive prehistoric bear that roamed Eurasia during the Middle and Late Pleistocene epoch, from about 300,000 years ago until its extinction around 24,000 years ago. This formidable creature was a prominent member of the Ice Age megafauna, coexisting with woolly mammoths, woolly rhinoceroses, and early humans across a vast geographical range. Despite its intimidating size, the cave bear's lifestyle and diet was surprisingly different from many modern large carnivores. One of the most striking features of the cave bear was its immense size. Adult males were considerably larger than modern grizzly bears and polar bears, often reaching lengths of up to 3.5 meters from nose to tail and standing over 1.7 meters tall at the shoulder when on all fours. Their weight could exceed 1,000 kilograms, making them truly colossal animals. Females were smaller, but still considerably larger than most modern bear species. Their skeletal structure was robust, with thick bones and powerful limbs, indicative of their massive build. The skull was particularly distinctive, featuring a steep, high forehead and a relatively short, broad snout, giving it a somewhat domed appearance compared to the flatter profile of modern bears. Despite its imposing size and the common misconception that it was a fierce predator, scientific evidence strongly suggests that the cave bear was predominantly herbivorous, meaning its diet consisted mainly of plants. Analysis of their teeth, particularly the wear patterns on their molars, indicates a diet rich in fibrous plant material. Their molars were broad and flat, well suited for grinding tough vegetation, rather than the sharp, shearing teeth found in carnivores. Isotope analysis of their bones, which examines the chemical composition of their diet over their lifetime, further supports a largely vegetarian lifestyle. They likely consumed a wide variety of plants available in their environment, including grasses, herbs, berries, and roots. While they might have occasionally supplemented their diet with insects or small amounts of carrion, meat was not a significant component of their diet. This makes them more akin to modern brown bears that primarily eat plants, rather than polar bears, which are largely carnivorous. The name cave bear is derived from the immense number of their fossilized remains found in caves across Europe and Asia. These caves were not just temporary shelters, but served as crucial sites for hibernation and raising cubs. During the long, harsh Ice Age winters, cave bears would retreat into these underground sanctuaries to enter a state of torpor, conserving energy when food was scarce. Many individuals would return to the same caves year after year. The accumulation of bones in these caves over thousands of years is testament to their consistent use. In some caves, thousands of individual cave bear skeletons have been discovered, forming deep layers of bone deposits. These sites provide invaluable information about their population dynamics, health, and behavior. The extensive use of caves also led to a unique interaction with early humans. Both cave bears and early human species, including Neanderthals and early modern humans, utilized caves for shelter. This would have led to competition for these valuable resources, especially during the winter months when bears sought hibernation sites. While direct evidence of large-scale conflict is limited, it is plausible that humans sometimes drove bears out of caves or scavenged their remains. Some archaeological sites show evidence of human activity alongside cave bear bones, suggesting that humans might have hunted younger or weaker bears, or more commonly, scavenged carcasses. The geographical range of the cave bear extended across much of Europe and parts of Asia, from Spain in the west to the Ural Mountains in the east, and as far north as the British Isles, and as far south as Italy and Greece. They inhabited a variety of environments within this range, including forests, open woodlands, and steppe tundra regions, as long as suitable caves were available for shelter and hibernation. Their presence is particularly well documented in mountainous regions with abundant limestone caves. The extinction of the cave bear around 24,000 years ago, before the last glacial maximum, is a subject of scientific study. Unlike many other megafauna that disappeared closer to 10,000 years ago, the cave bear's decline began earlier. Several factors are thought to have contributed to their demise. One major factor was climate change. As the climate became progressively colder and drier leading up to the last glacial maximum, the availability of their preferred plant foods, especially the more nutritious herbaceous plants, would have significantly diminished. The spread of cold, open steppe and tundra, with fewer diverse plant species, would have put immense pressure on a large herbivore like the cave bear. Another contributing factor was the loss of suitable hibernation sites. As glaciers expanded and permafrost spread, many caves may have become inaccessible or too cold and damp for hibernation. The reliance on caves for winter survival made them vulnerable to changes in their availability. Furthermore, competition with humans for cave resources might have played a role, though the extent of this impact is debated. While humans might have occasionally hunted them, the primary pressure was likely environmental. The cave bear's specialized diet and strong reliance on caves for survival made it particularly susceptible to the environmental shifts of the late Pleistocene, ultimately leading to its extinction. The vast fossil record of the cave bear continues to provide scientists with a wealth of information about Ice Age ecosystems and the dynamics of prehistoric life. The woolly rhinoceros, Chelodonta antiquitatis, was a large herbivorous mammal that thrived across the cold, open landscapes of Eurasia during the Pleistocene epoch, from about 350,000 years ago until its extinction around 14,000 years ago. This formidable animal was a quintessential inhabitant of the Ice Age, perfectly adapted to the harsh, frigid conditions of the steppe tundra environment. Its robust build, thick fur and distinctive horn made it a prominent member of the megafauna that characterized the glacial periods. The most defining physical characteristic of the woolly rhinoceros was its dense, shaggy coat of fur, which provided essential insulation against the extreme cold. This fur was long and thick, covering its entire body, including its legs and ears, much like the woolly mammoth. The colour of its fur is thought to have been a reddish-brown or dark brown, based on preserved remains and cave paintings. Beneath this outer layer of long guard hairs, there was likely a dense undercoat, similar to that of modern musk oxen, trapping warm air close to the skin. This thick fur, combined with a substantial layer of subcutaneous fat, allowed the woolly rhino to maintain its body temperature in environments where temperatures frequently dropped far below freezing. Another prominent feature was its two horns, made of keratin, the same material as human fingernails and hair. Unlike modern African rhinos, the woolly rhino possessed two horns, arranged one behind the other on its snout. The front horn was significantly larger and longer, often reaching lengths of up to 1 meter, and was flattened from side to side, giving it a blade-like appearance. The second horn, located behind the first, was much smaller. These horns were not used for fighting predators in the same way a modern rhino might use its horn to gore. Instead, the large flattened front horn is believed to have been primarily used for sweeping snow aside to uncover vegetation during winter, a behaviour known as snow ploughing or snow shoveling. This adaptation was crucial for accessing food in snow-covered landscapes, allowing them to survive in areas where other large herbivores might have struggled. The body of the woolly rhinoceros was heavily built and powerful, well suited for traversing rugged frozen terrain. They stood about 2 meters tall at the shoulder and could reach lengths of up to 4 meters, weighing between 2,000 and 3,000 kilograms. Their legs were short and stout, providing stability on uneven ground. A distinctive hump of muscle and fat was present over their shoulders, likely serving as an energy reserve, similar to the hump on a bison, and possibly helping to support their massive head and horn when foraging in snow. Their ears were relatively small, another adaptation to minimize heat loss in cold environments. The diet of the woolly rhinoceros consisted mainly of grasses and sedges. They were grazers, adapted to feeding on the tough, low-growing vegetation of the steppe tundra. Their teeth were high-crowned and strong, designed for grinding abrasive plant material. Evidence from their fossilized teeth and preserved stomach contents confirms their diet of fibrous plants. They would have grazed extensively across the vast open plains, constantly moving to find new patches of vegetation. Their ability to use their specialized horn to clear snow was a key factor in their survival during the long, harsh Ice Age winters, allowing them to access food that was otherwise buried. Woolly rhinos were solitary animals or lived in small family groups, unlike the large herds of woolly mammoths. This behaviour is consistent with modern rhinoceros species. They would have defended themselves against predators like cave lions and wolves using their immense size and powerful build, rather than relying on their horns for direct combat. Their thick skin and robust frame would have provided a significant defence against attacks. The geographical distribution of the woolly rhinoceros was extensive across Eurasia. Their fossils and remains have been found from Western Europe, including the British Isles, across Siberia, and into northern China and Korea. They were particularly abundant in the vast, cold steppe tundra regions that characterized much of northern Eurasia during glacial periods. Their range largely overlapped with that of the woolly mammoth, indicating that they shared similar habitat preferences for cold, open grasslands. Remarkably well-preserved carcasses of woolly rhinos, complete with fur and soft tissues, have been discovered in the permafrost of Siberia, providing invaluable insights into their anatomy and adaptations. These discoveries, like the famous Sasha and Tima rhino calves, offer a rare glimpse into the appearance and biology of these extinct giants. The extinction of the woolly rhinoceros occurred around 14,000 years ago, at the end of the last glacial period, slightly earlier than the final disappearance of the woolly mammoth. Their extinction is believed to be primarily driven by rapid climate change and the resulting habitat loss. As the Earth warmed at the beginning of the Holocene epoch, the vast steppe tundra environment, which was their primary habitat, began to shrink. Forests and woodlands expanded into areas that were once open grasslands, and wetlands increased. The woolly rhino, being a specialized grazer of open, cold environments, struggled to adapt to these rapidly changing conditions. Their specialized horn for snowplowing became less useful as snow cover diminished, and new vegetation types emerged. While climate change and habitat loss are considered the main drivers, human hunting pressure may also have played a role, especially as human populations expanded and perfected their hunting techniques. Evidence from archaeological sites suggests that early humans did hunt woolly rhinos, as their bones are found alongside human tools. However, given their large size and solitary nature, they might have been less frequently hunted than herd animals like mammoths or bison. Ultimately, the woolly rhinoceros's specialized adaptations, which allowed it to thrive in the extreme cold of the Ice Age, became a disadvantage as the climate warmed, leading to its eventual disappearance from the planet. It remains a powerful symbol of the unique megafauna that once roamed the ancient world. The Irish elk, Megaloceros giganteus, is one of the most magnificent and enigmatic creatures of the Ice Age, renowned for its truly enormous antlers. Despite its common name, it was neither exclusively Irish nor a true elk in the modern sense. It was a species of deer, more closely related to fallow deer than to the modern elk or moose. This grand herbivore roamed across Eurasia during the late Pleistocene epoch, from about 400,000 years ago until its final extinction around 7,700 years ago. Its immense antlers are the largest known of any deer species, making it a spectacular example of extreme evolutionary adaptation. The most striking and iconic feature of the Irish elk was undoubtedly its antlers. These were of colossal size, far exceeding those of any living deer. A fully grown male's antlers could span up to 3.6 meters from tip to tip and weigh as much as 40 kilograms. These antlers were broad and palmated, meaning they had flattened hand-like sections with multiple tines, rather than simple branches. Like all deer, the Irish elk shed its antlers annually, typically in spring, and regrew them over the summer, a process that would have required an immense amount of energy and nutrients, particularly calcium. The sheer scale of these antlers is what captures the imagination and has driven much scientific inquiry into their purpose and the reasons for their development and eventual disappearance. The body size of the Irish elk was also impressive, though not as extreme as its antlers. Males stood about 2.1 meters tall at the shoulder, making them comparable in size to a large modern moose. Females were smaller and possessed no antlers. Their skeletal structure was robust, built to support the enormous weight of the antlers and to navigate the open environments they inhabited. Their overall build was powerful, with long legs and a strong neck, necessary for carrying and maneuvering their massive headgear. Their coat colour is unknown, but it was likely a shade of brown, suitable for camouflage in their grassland and woodland habitats. The primary function of the Irish elk's enormous antlers is believed to have been for sexual display and competition among males. In many deer species, antler size is a direct indicator of a male's health, strength, and genetic fitness. Larger antlers signal to females that a male is a desirable mate, capable of acquiring sufficient resources to grow such an extravagant display. They also served as weapons in ritualized combat between rival males during the breeding season, or rut. Males would lock antlers and push against each other, attempting to overpower their opponent and gain access to females. The broad, palmated shape of the antlers would have been effective in these pushing contests, providing a large surface area for locking and leverage. While they might have offered some defense against predators, their primary role was almost certainly in intraspecific competition and mate attraction. The diet of the Irish elk was primarily herbivorous. Analysis of their teeth and fossilized pollen found with their remains suggests they were both grazers and browsers, meaning they ate both grasses and the leaves and shoots of trees and shrubs. They likely preferred a mixed diet, taking advantage of the diverse vegetation available in their habitats. During the spring and summer, when antlers were growing, males would have required a particularly rich diet to obtain the massive amounts of calcium and other nutrients needed for antler growth. This high energy demand meant they would have favoured environments with abundant and nutritious plant life. The geographical distribution of the Irish elk was widespread across Eurasia, from Ireland in the west, across mainland Europe, and into parts of Asia, including Siberia and China. They inhabited a variety of environments, including open grasslands, woodlands, and forest margins. Their presence in Ireland, where many well-preserved skeletons have been found in peat bogs, is why they received the Irish part of their common name, even though their range was much broader. These bog finds, often complete skeletons, have provided invaluable insights into their anatomy and life history. The extinction of the Irish elk is a classic case study in paleontology, with much debate surrounding the reasons for its demise. The species persisted through multiple glacial and interglacial cycles of the Pleistocene, adapting to changing environments. However, its final extinction occurred relatively late in the Ice Age, around 7,700 years ago, well after the last glacial maximum and after many other megafauna had already disappeared. This timing suggests that factors other than just the initial warming at the end of the glacial period were at play. One leading hypothesis for their extinction points to habitat change. As the Earth warmed and the climate became more humid at the beginning of the Holocene epoch, the open grasslands and mixed woodlands that the Irish elk preferred began to be replaced by denser forests. The immense antlers, while advantageous in open environments for display and combat, would have become a significant hindrance in dense forests, making movement difficult and potentially trapping males in thick undergrowth. This shift in vegetation would have reduced their preferred foraging grounds and made their specialized adaptations less effective. Another significant factor is the calcium stress hypothesis. The growth of such massive antlers each year required an enormous intake of calcium and other minerals. As the climate changed and forests replaced grasslands, the availability of calcium-rich plants in their diet might have decreased. Additionally, the soil chemistry in newly forested areas might have been different, leading to plants with lower mineral content. If males could not obtain enough calcium, they would have been unable to grow impressive antlers, which would have severely impacted their ability to attract mates and reproduce, leading to a decline in population. Finally, human hunting pressure is also considered a contributing factor. While not the sole cause, early human populations were expanding and becoming increasingly skilled hunters during the period of the Irish elk's decline. The large size of the Irish elk would have made it an attractive target for hunters, providing a significant source of meat and hides. The combination of environmental changes, particularly habitat alteration, and potential nutritional stress related to antler growth, coupled with increasing human hunting, likely pushed the Irish elk to extinction. The Irish elk stands as a powerful example of how even highly successful and specialized species can be vulnerable to rapid environmental shifts and new pressures. The disappearance of the large animals known as Megafauna at the end of the last ice age represents one of the most significant and perplexing extinction events in Earth's recent history. Across every continent except Antarctica, a vast array of impressive creatures vanished, including woolly mammoths, saber-toothed cats, giant ground sloths, woolly rhinoceroses, cave bears, and many others. This wave of extinctions primarily occurred between about 50,000 and 10,000 years ago, with a particularly intense phase around 12,000 to 10,000 years ago, coinciding with the end of the Pleistocene epoch and the transition into the current Holocene epoch. The precise reasons for this widespread demise have been a subject of intense scientific debate for decades, with two main hypotheses dominating the discussion: rapid climate change and human hunting. The climate change hypothesis posits that the dramatic warming and environmental shifts at the end of the last glacial period were the primary drivers of megafaunal extinction. As the Earth transitioned from a cold, glacial state to a warmer, interglacial one, global temperatures rose significantly. This warming led to the melting of vast continental ice sheets, causing sea levels to rise and inundate coastal plains. More importantly for terrestrial animals, the melting ice and changing temperatures profoundly altered vegetation patterns and habitats. The expansive, cold and relatively dry steppe tundra environments, which supported many of the megafauna, began to shrink. These open grasslands and shrublands were gradually replaced by denser forests and woodlands in many regions, particularly in parts of Europe and North America. This habitat fragmentation and loss would have severely impacted species specialized for open environments. For example, large grazers like woolly mammoths, adapted to feeding on vast quantities of grasses and sedges, would have struggled to find sufficient food in newly emerging forests. The Irish elk, with its enormous antlers, would have found dense forests difficult to navigate and forage within. Beyond direct habitat loss, climate change also led to other ecological disruptions. Changes in precipitation patterns, including shifts in rainfall and snowfall, could have affected water availability and plant growth. The formation of new wetlands and lakes, while providing some resources, could also have created barriers or changed migration routes for large animals. Furthermore, the rapid nature of some of these climate shifts, such as the Younger Dryas event around 12,900 to 11,700 years ago, represented periods of abrupt cooling and environmental instability. Such rapid fluctuations could have put immense stress on species already struggling to adapt to overall warming trends. Large animals, often characterized by slower reproductive rates and longer generation times, are generally less able to adapt quickly to rapid environmental changes compared to smaller, faster reproducing species. Their specialized diets or habitat requirements could also make them particularly vulnerable to even subtle shifts in their ecosystems. The human hunting hypothesis, also known as the overkill hypothesis, proposes that the expansion of early human populations, particularly Homo sapiens, across continents was the primary cause of megafaunal extinctions. As humans migrated into new territories, they encountered large animals that had no prior experience with human predators and therefore lacked innate fear or effective defensive strategies against them. These animals, often large and slow-moving, would have represented easily accessible and highly rewarding prey for skilled human hunters. The hypothesis suggests that human hunting pressure, even from relatively small populations, could have been sufficient to decimate megafaunal populations, especially if those populations were already stressed by other factors. Evidence supporting the overkill hypothesis includes the strong correlation between the arrival of humans on a continent and the subsequent wave of megafaunal extinctions. For instance, in North America, the vast majority of megafauna disappeared shortly after the arrival of the Clovis people, around 13,500 to 13,000 years ago. Similarly, in Australia, a significant number of large marsupials and reptiles vanished around 50,000 years ago, roughly coinciding with the earliest evidence of human presence on the continent. In South America, extinctions also followed the human colonization wave. Furthermore, archaeological sites often show evidence of humans hunting megafauna, including butchered bones, projectile points embedded in skeletons, and large kill sites. The argument is that humans, with their advanced tools, cooperative hunting strategies, and ability to adapt to diverse environments, represented a novel and highly effective predator that many megafauna were simply not equipped to survive. While these two hypotheses have often been presented as competing explanations, a growing consensus among scientists favours a two-punch or synergistic model, suggesting that both climate change and human hunting acted in concert to drive the extinctions. In this view, climate change created environmental stress, leading to reduced megafaunal populations, fragmented habitats, and increased vulnerability. These already weakened populations then faced additional, perhaps decisive, pressure from human hunting. For example, a population of mammoths might have been struggling due to shrinking grasslands. If human hunters then targeted these stressed herds, even a moderate level of hunting could have pushed them past a critical threshold, leading to their collapse. This combined impact would have been far more devastating than either factor acting alone. Consider the case of the woolly mammoth. As the Ice Age ended, their preferred steppe tundra habitat was replaced by forests and bogs, reducing their food supply and fragmenting their populations. Simultaneously, human populations were expanding and becoming highly effective mammoth hunters, as evidenced by numerous archaeological sites with mammoth remains. It is likely that the combination of these pressures proved insurmountable for the species. Similarly, for the saber-toothed cats, their reliance on large, slow prey meant that as their food sources declined due to environmental changes and human hunting, they themselves would have faced starvation. Their specialized hunting adaptations, so effective for large prey, became a disadvantage when smaller, faster animals became the dominant herbivores. Other contributing factors, though generally considered secondary, may also have played a role. Disease could have been a factor, potentially introduced by humans or their domesticated animals, or emerging from changing environmental conditions. However, direct evidence for widespread disease outbreaks causing mass extinctions is difficult to find in the fossil record. Asteroid impacts have been proposed for some extinction events, but there is no strong evidence for a major impact coinciding with the late Pleistocene megafauna extinctions. The loss of genetic diversity in already declining populations could have made them more susceptible to environmental changes or disease. The varying timing of extinctions across different continents also provides clues. In Australia, where humans arrived very early, around 50,000 years ago, extinctions occurred much earlier than in North America. This suggests that in some regions, human impact might have been the dominant factor, especially if the megafauna had evolved in isolation from human predators for millions of years. In contrast, in Eurasia, where humans had coexisted with megafauna for much longer, the extinctions appear to be more closely tied to the final rapid warming at the end of the last glacial period, suggesting climate change played a more prominent role, or that the megafauna had already developed some adaptations to human hunting pressure. The extinction of the megafauna had profound ecological consequences. The removal of these large herbivores and carnivores drastically altered ecosystems. For example, the loss of large grazers like mammoths would have changed vegetation structure, allowing forests to expand more rapidly. The disappearance of large predators would have affected the populations of smaller herbivores. The landscape itself was transformed as the agents of disturbance, like mammoth trampling, were removed. Understanding this extinction event is crucial, not only for historical context, but also for informing modern conservation efforts, as it highlights the vulnerability of a large-bodied species to rapid environmental change and human pressures. The mystery of the megafauna extinction continues to be a rich area of research, with ongoing discoveries and refined analyses constantly adding to our understanding of this pivotal moment in Earth's biological history. Life for early humans during the Ice Age was a constant challenge, demanding remarkable adaptability, ingenuity, and resilience. Our ancestors, primarily Homo sapiens and earlier Homo species, faced a world dramatically different from our own, characterized by extreme cold, vast ice sheets, and landscapes teeming with formidable megafauna. Survival depended on their ability to master their environment, develop sophisticated tools, and cooperate within their social groups. One of the most fundamental challenges was the cold climate. During glacial periods, temperatures across much of Eurasia and North America were far below freezing for extended periods. To survive, early humans developed sophisticated strategies for shelter and clothing. Caves were invaluable natural shelters, offering protection from the elements, predators, and providing a relatively stable temperature. Archaeological evidence shows extensive use of caves, with layers of occupation spanning thousands of years. When caves were not available, humans constructed temporary or semi-permanent dwellings. These could range from simple windbreaks to more elaborate structures. In some regions, particularly in Eastern Europe, evidence suggests the construction of huts made from the bones and hides of woolly mammoths. These structures, often circular or oval, used mammoth tusks as supports for roofs and large bones as foundations, with hides draped over them to create enclosed spaces. These dwellings were likely insulated with animal furs, moss or earth to retain heat. clothing was absolutely essential for survival in the frigid Ice Age. Early humans learned to process animal hides into warm, durable garments. This involved scraping hides clean, softening them through various methods, and then cutting and sewing them together. Bone needles, sometimes with eyes fine enough for delicate stitching, have been found at archaeological sites, indicating sophisticated tailoring. Clothing would have consisted of multiple layers, including tunics, trousers, and hooded parkas, all made from the furs and skins of animals like reindeer, mammoth, and Arctic fox. Footwear, likely fur-lined boots, would have protected against frostbite. This ability to create tailored, multi-layered clothing was a critical innovation, allowing humans to expand into colder regions and survive through harsh winters. The mastery of fire was another cornerstone of Ice Age survival. Fire provided essential warmth, allowing humans to survive in otherwise uninhabitable cold environments. It also offered protection from large predators, keeping them at bay during the night. Beyond warmth and safety, fire was crucial for cooking food. Cooking made tough meat and fibrous plants more digestible, increasing nutrient absorption and reducing the risk of parasites. This improved diet contributed to brain development and overall health. Fire was also used for tool making, such as hardening wooden spear tips or making flint easier to flake by heat treatment. The ability to control and maintain fire was a complex skill, requiring knowledge of fuel sources and ignition techniques, and it fundamentally transformed human life. Hunting was a primary means of acquiring food and resources. Ice Age humans were skilled hunters, targeting a wide range of animals, from large megafauna to smaller game. Their prey included woolly mammoths, woolly rhinoceroses, bison, reindeer, wild horses, and various deer species. Hunting large animals required cooperation and sophisticated strategies. Hunters would work together to corner, drive, or ambush prey. They used a variety of weapons, including spears tipped with sharpened stone points, like the distinctive Clovis points in North America, atlatls, spear throwers, to increase throwing power and range, and possibly bows and arrows in later periods. The kill was not just for meat. Every part of the animal was utilized. Hides were used for clothing and shelter, bones for tools and construction, sinews for lashing, and fat for fuel and food. While hunting large animals was vital, early humans also engaged in gathering plants, roots, berries, and nuts, depending on seasonal availability and regional climate. Fishing and fowling also contributed to their diet, especially in areas near water bodies. Their diet was diverse and adaptable, reflecting their opportunistic approach to foraging in varied environments. The ability to store food, such as drying meat or preserving fat, would have been crucial for surviving periods of scarcity, particularly during winter. Tool technology was continually evolving and becoming more refined during the Ice Age. Early humans developed a wide array of stone tools, including hand axes, scrapers, blades, and projectile points. These tools were made by carefully flaking and shaping various types of stone, such as flint and chert. Beyond stone, they also utilized bone, antler, and ivory to create specialized tools like needles, awls, harpoons, and spear throwers. The development of composite tools, where different materials were combined, e.g. a stone point hafted onto a wooden spear, represented a significant technological leap. These tools allowed them to butcher large animals efficiently, process hides, work wood, and perform a variety of daily tasks essential for survival. Social structure among early humans was likely based on small nomadic bands or extended family groups. These groups would have moved across the landscape, following animal migrations and seasonal availability of resources. Cooperation within the group was paramount for hunting, defense, and sharing resources. The division of labor, with some individuals focusing on hunting, others on gathering, and still others on tool-making or childcare, would have been common. Evidence from archaeological sites suggests that these groups were interconnected, with materials like stone tools or shells found far from their geological source, indicating trade networks or long-distance travel. Beyond the purely practical aspects of survival, early human life also encompassed a rich cultural and symbolic dimension. The Ice Age saw the emergence of incredible cave art, particularly in Europe, depicting animals like mammoths, bison, horses, and rhinos, as well as abstract symbols and human figures. These artworks, often found deep within caves, suggest complex belief systems, rituals, and a deep connection to the natural world. Portable art, such as carved figurines of animals or human forms, like the famous Venus figurines, also indicates a flourishing artistic expression. The presence of personal adornments, like beads made from shells or animal teeth, suggests an interest in aesthetics and perhaps social signalling. Burial practices, sometimes involving grave goods or ochre, suggest a concern for the deceased and possibly beliefs about an afterlife. The migration patterns of early humans during the Ice Age were extensive. Homo sapiens originated in Africa and began to spread out into Eurasia and beyond. Their ability to adapt to colder climates, facilitated by clothing, fire, and advanced hunting techniques, allowed them to colonize vast new territories. The lowering of sea levels during glacial periods created land bridges, most notably the Bering Land Bridge between Asia and North America, which allowed humans to cross into the Americas for the first time, around 15,000 to 20,000 years ago. This global dispersal of humans, driven by resource availability and population growth, was a defining characteristic of the late Ice Age. Neanderthal people, Homo neanderthalensis, represent an extinct species or subspecies of archaic humans who inhabited Eurasia from about 400,000 years ago until their disappearance around 40,000 years ago. They are our closest extinct relatives, sharing a common ancestor with modern humans, Homo sapiens, and coexisting with them for thousands of years in parts of Europe and Asia. The study of Neanderthals provides crucial insights into human evolution, adaptation to Ice Age environments, and the complex interactions between different human groups. Neanderthals possessed distinct physical features that set them apart from modern humans. They were generally shorter and stockier than Homo sapiens, with robust, heavily muscled bodies. Their bones were thicker and denser, indicating immense strength, an adaptation likely suited for the physical demands of their Ice Age lifestyle, including close-quarters hunting. Their skulls were characterized by a prominent brow ridge above the eyes, a receding forehead, and a large, often elongated brain case that was, on average, slightly larger than that of modern humans. They had a distinctive mid-facial prognathism, meaning their mid-face projected forward, and a broad nose. Their lack of a prominent chin was another distinguishing feature. These physical traits are often interpreted as adaptations to cold climates, with the robust build helping to conserve heat, and the large nasal passages potentially warming and humidifying cold, dry air before it reached the lungs. Neanderthals were highly skilled toolmakers, primarily associated with the Mousterian stone tool industry. This technology involved a sophisticated method called the Levallois technique, where a stone core was carefully prepared before a single, predetermined flake was struck off. This technique allowed for the production of sharp, efficient flakes that could be used as scrapers, points, and knives. Mousterian tools were versatile and effective for a variety of tasks, including butchering animals, scraping hides, and working wood. While their tools were generally less varied and complex than the later Upper Paleolithic tools of Homo sapiens, they were perfectly adequate for their survival needs and represented a significant technological advancement over earlier stone tool traditions. Neanderthals were expert hunters, primarily targeting large and medium-sized mammals that roamed the Ice Age landscapes. Their prey included woolly mammoths, woolly rhinoceroses, bison, wild horses, and various deer species. Evidence from archaeological sites, such as bone accumulations with cut marks, indicates that Neanderthals were capable of systematically hunting and butchering large animals. Their hunting strategy likely involved close-quarters encounters, using thrusting spears rather than projectile weapons that could be thrown from a distance. This is supported by the high incidence of healed bone fractures found on Neanderthal skeletons, injuries consistent with those seen in modern rodeo riders, suggesting frequent close encounters with large, dangerous animals. They were efficient at exploiting their environment for food, and their diet was heavily reliant on meat, though they also consumed plants, as evidenced by analysis of dental plaque. The geographical range of Neanderthals extended across Europe, the Middle East, and parts of Central Asia. They adapted to a wide range of environments, from the cold, open-steppe tundra of northern Europe to the more temperate woodlands and Mediterranean climates of the south, and even mountainous regions. Their presence in diverse habitats demonstrates their flexibility and ability to survive in varied ecological niches during fluctuating glacial and interglacial periods. Neanderthals used fire extensively for warmth, cooking and protection, just like modern humans. Evidence of hearths and charred bones is common at Neanderthal sites, indicating their control over fire. They also sought shelter in caves and rock shelters, which provided natural protection from the elements and predators. While they did not build complex structures like the mammoth bone huts of some Homo sapiens groups, they modified their cave dwellings, creating activity areas and possibly simple partitions. Beyond their practical skills, there is growing evidence for complex behaviours and symbolic thought among Neanderthals. While once viewed as primitive, archaeological discoveries increasingly reveal a more nuanced picture. There is evidence of burial practices, with some individuals found in graves that suggest intentional interment, sometimes with grave goods or flowers, although the interpretation of these findings is debated. They used pigments like ochre, possibly for body adornment or symbolic purposes. They collected unusual objects such as shells and raptor claws, which they sometimes modified, suggesting an aesthetic sense or symbolic meaning. There is also limited evidence for the use of jewellery or personal ornaments. While not as abundant or diverse as the art of Homo sapiens, these findings challenge earlier notions of Neanderthals as purely utilitarian beings. The interaction between Neanderthals and early Homo sapiens is a critical aspect of their story. Modern humans, having originated in Africa, began to expand into Eurasia, encountering Neanderthal populations. These two groups coexisted in some regions for thousands of years. Genetic studies have revealed that interbreeding occurred between Neanderthals and Homo sapiens, as evidenced by the presence of Neanderthal DNA in the genomes of most non-African modern human populations. This indicates that they were capable of successful reproduction, and that at least some level of cultural exchange or interaction took place. The extinction of Neanderthals around 40,000 years ago is a complex and highly debated topic. Several hypotheses have been proposed, often overlapping. One major theory suggests that climate change played a significant role. The period leading up to their extinction was characterized by increasing climate instability and rapid, severe fluctuations between cold and slightly warmer conditions. Neanderthals, with their specialized adaptations to cold and reliance on specific hunting strategies, may have struggled to adapt to these rapid environmental shifts, particularly as their preferred habitats fragmented. Another prominent hypothesis points to competition with Homo sapiens. Modern humans, arriving in Eurasia, may have had certain advantages. These could include a more flexible diet, a broader range of tool technologies, including projectile weapons like bows and arrows, which allowed for safer, long-distance hunting, more complex social networks, and potentially a greater capacity for symbolic thought and innovation. Even if Homo sapiens did not directly outcompete Neanderthals in every aspect, a slight competitive edge in resource acquisition or reproductive success over thousands of years could have led to the gradual decline of Neanderthal populations. The competitive exclusion model suggests that even a small difference in efficiency could lead to one species replacing another over time. Other factors, such as disease, perhaps introduced by Homo sapiens, low population numbers and genetic isolation, leading to reduced genetic diversity, and even assimilation into larger Homo sapiens populations through interbreeding, are also considered. It is highly probable that no single factor caused their extinction, but rather a combination of environmental pressures, competition, and demographic vulnerabilities, perhaps exacerbated by their interactions with the expanding populations of Homo sapiens. The legacy of Neanderthals is profound. They were a highly successful human species, adapting to and thriving in the challenging Ice Age environments for hundreds of thousands of years. Their sophisticated tools, hunting prowess, and emerging evidence of complex behaviours continue to reshape our understanding of human evolution and the diversity of the human story. Their disappearance marks a significant turning point, leaving Homo sapiens as the sole surviving human species on Earth. Ice Age cave art represents one of humanity's earliest and most profound forms of artistic expression, a vivid window into the minds and lives of our ancestors who lived tens of thousands of years ago. These remarkable paintings, engravings and sculptures are predominantly found in caves and rock shelters across Europe, particularly in France and Spain, but also in other parts of the world, including Asia and Australia. The vast majority of the well-known European cave art dates from the Upper Paleolithic period, roughly from 40,000 to 10,000 years ago, coinciding with the latter part of the last ice age. These artworks were not mere decorations, they were deeply meaningful creations reflecting the beliefs, observations and perhaps rituals of the people who made them. The subjects depicted in Ice Age cave art are overwhelmingly animals. The artists showed a keen observational skill and an intimate knowledge of the fauna that shared their world. Common animal subjects include the powerful Megafauna of the Ice Age, woolly mammoths, woolly rhinoceroses, bison, both European steppe bison and American bison, horses, often depicted with shaggy manes and tails, reindeer, and various species of deer. Predators such as cave lions, bears, including cave bears, and wolves are also depicted, though less frequently than herbivores. Birds, fish, and even insects are rare, but occasionally present. The animals are often rendered with remarkable realism and dynamism, conveying a sense of movement and life. Artists frequently use the natural contours of the cave walls to enhance the three-dimensional quality of their animal figures, making a bulge in the rock become the shoulder of a bison or the flank of a horse. The accuracy of these depictions has allowed modern scientists to identify extinct species and even infer aspects of their behaviour and appearance. For example, the detailed depictions of woolly mammoths confirm their shaggy coats and distinct body shapes. While animals dominate, human figures are surprisingly rare and often depicted in a highly stylized or abstract manner, unlike the realistic animal portrayals. When humans do appear, they're often schematic, sometimes appearing as stick figures or composite beings with animal features, perhaps representing shamans or spirits. Handprints, both positive, painted on, and negative, stenciled by blowing pigment around a hand, are also common, serving as a direct personal signature of the artists or participants in rituals. These handprints are often found in clusters, suggesting communal activity or repeated visits. Beyond animals and humans, a significant portion of Ice Age cave art consists of abstract signs and symbols. These geometric shapes include dots, lines, grids, circles, triangles, and various other non-representational marks. The meaning of these signs is largely unknown and remains a subject of intense speculation. Some theories suggest they might represent territorial markers, clan symbols, numerical tallies, astronomical observations, or even early forms of writing or mnemonic devices. Their consistent recurrence across different sites suggests they held shared meanings within and between various groups of Ice Age people. The study of these abstract signs is crucial for understanding the full symbolic complexity of Ice Age art. The techniques and materials used by Ice Age artists were remarkably sophisticated for their time. Pigments were derived from natural minerals found in the environment. Red, yellow and brown colours came from various forms of ochre, an iron oxide mineral. Black pigments were typically made from manganese dioxide or charcoal, burnt wood or bone. White was sometimes obtained from kaolin clay or ground calcite. These pigments were ground into fine powders and then mixed with binders, such as animal fat, blood or water, to create paint. The paint was applied to the cave walls using various methods. Artists used their fingers, chewed sticks that served as brushes, or pads of moss or fur. For fine lines, sharpened bone or stone tools might have been used for engraving. One particularly ingenious technique involved blowing powdered pigment through a hollow bone or reed, creating a spray paint effect, often used for stenciling handprints or creating soft outlines. Engravings were made by scratching or cutting into the rock surface with sharp flint tools. In some cases, artists would first engrave an outline and then fill it with paint. The locations of the artworks within caves are also significant. While some art is found near cave entrances, much of the most spectacular and well-preserved art is located deep within the caves, in chambers and passages that are difficult to access, requiring light sources and navigation through dark, often treacherous terrain. This suggests that the creation and viewing of these artworks were not casual activities, but possibly part of specific rituals or ceremonies. The darkness and isolation of these deep chambers would have enhanced the sensory experience, making the flickering light of a torch illuminate the painted figures in a dynamic, almost living way. The acoustics of certain chambers might also have played a role, with sounds echoing or reverberating in specific ways. The purpose and meaning of Ice Age cave art are subjects of ongoing scholarly debate, with no single, universally accepted explanation. Several theories have been proposed. One of the oldest and most popular theories is hunting magic. This idea suggests that the paintings were created as part of rituals intended to ensure successful hunts. By depicting animals, especially those that were hunted for food, the artist might have believed they were gaining power over the animals or guaranteeing their abundance. Wounded animals or animals with spears depicted on them could support this idea. Another theory relates to fertility rituals. The art might have been intended to promote the fertility of the animals, ensuring a continuous supply of food for the community. The depiction of pregnant animals or animals in mating postures could be interpreted in this light. The shamanistic theory proposes that the caves were sacred spaces, and the art was created by shamans or spiritual leaders as part of trance states or visions. The abstract signs might represent altered states of consciousness, and the animals could be spirit helpers or guides. The deep, dark, and acoustically resonant parts of caves could have been ideal settings for such spiritual experiences. Some scholars suggest that the art served as a form of communication or storytelling. The images might have recorded important events, transmitted knowledge about animal behaviour, or served as visual narratives for teaching younger generations. They could have been a way to pass down cultural traditions and information vital for survival. The art might also have played a role in social cohesion and group identity. The act of creating and viewing the art together could have strengthened community bonds, reinforced shared beliefs, and marked a group's territory or identity. The presence of common symbols across different sites could indicate shared cultural practices over wide areas. More recent interpretations include the possibility of astronomical observations, with some patterns of dots and lines being interpreted as rudimentary star maps or calendars, possibly tracking seasonal changes important for hunting. Other theories suggest the art was related to initiation rites for young members of the community, guiding them through a symbolic journey into adulthood and imparting knowledge. It is highly probable that there was no single purpose for all Ice Age cave art. Different artworks in different locations, or even within the same cave, might have served multiple functions, reflecting the complex and multifaceted belief systems of the people who created them. The art was likely deeply integrated into their daily lives and spiritual world. The skill and dedication required to create these artworks are astounding. Artists had to navigate deep, dark cave passages, often climbing or squeezing through tight spaces, carrying their materials and light sources such as stone lamps burning animal fat. They worked on uneven, often damp surfaces, sometimes in difficult postures. The precision of their lines, the understanding of animal anatomy, and the effective use of colour and light demonstrate a high level of artistic mastery and a deep commitment to their craft. The fact that many of these artworks have survived for tens of thousands of years is a testament to the artist's choice of durable materials and the stable conditions within the caves. Famous sites like Lascaux in France, discovered in 1940, are renowned for their vibrant and dynamic depictions of horses, bison, stags, and aurochs, particularly in the Hall of Bulls. Chauvet Cave, also in France, discovered in 1994, contains some of the oldest and most breathtaking art, dating back over 30,000 years, featuring incredibly realistic and powerful images of cave lions, woolly rhinoceroses, and bears, often showing a mastery of perspective and shading. Altamira in Spain, discovered in 1879, is famous for its magnificent ceiling of polychrome bison, depicted with remarkable three-dimensionality. These sites, along with hundreds of others, continue to reveal new insights into the artistic and intellectual capabilities of our Ice Age ancestors. The preservation of these artworks, often due to the stable temperature and humidity within the caves, allows us to connect directly with the creative spirit of people who lived in a world long past. Ancient tools were fundamental to the survival and success of Ice Age humans, enabling them to adapt to diverse and challenging environments. From the earliest stone flakes to sophisticated composite weapons, the development and refinement of tools represent a continuous story of human ingenuity and cognitive advancement throughout the Pleistocene epoch. These tools allowed our ancestors to hunt, process food, create clothing, build shelters, and ultimately thrive in a world populated by formidable megafauna and extreme climates. The raw materials for ancient tools were primarily sourced from the natural environment. Stone was the most common material, particularly fine-grained brittle rocks that could be flaked to produce sharp edges. Flint and chert were highly prized due to their predictable fracturing properties. Other stones like obsidian, a volcanic glass, quartzite, and basalt were also used depending on regional availability. Beyond stone, bone, antler, and ivory, especially mammoth ivory, became increasingly important, particularly in later periods of the Ice Age, as they could be shaped into more specialised and durable implements. Wood was undoubtedly used extensively for shafts of spears, digging sticks, and other perishable items, though its preservation in the archaeological record is rare. The evolution of stone tool technologies during the Ice Age can be broadly categorised into several distinct industries, each representing a significant leap in complexity and efficiency. The earliest stone tool industry, dating back over 2.5 million years, is the Oldowan industry, associated with early Homo species. These tools were very simple, consisting primarily of choppers made by striking a few flakes off a rounded pebble to create a sharp edge. The flakes themselves were also used as cutting tools. These basic tools were effective for tasks like breaking open animal bones to access marrow or cutting meat. Following the Oldowan, the Acheulean industry emerged around 1.7 million years ago and persisted for over 1 million years. Its hallmark tool is the hand axe, a distinctive teardrop-shaped biface, worked on both sides, that was carefully shaped to create a sharp edge around its entire circumference. Acheulean hand axes were remarkably symmetrical and showed a greater degree of planning and skill than Oldowan tools. They were versatile, likely used for butchering large animals, digging, and perhaps even as cores for producing flakes. The Mousterian industry, primarily associated with Neanderthals and some early Homo sapiens, dominated from about 300,000 to 40,000 years ago. A key innovation of the Mousterian was the Levallois technique. This involved carefully preparing a stone core by shaping its edges and surface, so that when a single, powerful blow was struck, a predetermined sharp flake of a specific size and shape would detach. This allowed for more efficient and predictable production of flakes, which were then further retouched into various specialised tools like scrapers for processing hides, points for spear tips, and knives. Mousterian tools were highly effective for close-range hunting and processing large game. The Upper Paleolithic industries, beginning around 45,000 years ago and primarily associated with Homo sapiens, marked a period of rapid innovation and diversification in tool technology. These industries include the Aurignacian, Gravettian, Solutrean, and Magdalenian. A defining characteristic was the production of blades, long, narrow flakes that were at least twice as long as they were wide, offering a much greater cutting edge per unit of raw material. Blades were then further modified into a wide array of specialised tools. Burins were chisel-like tools used for engraving bone, antler and ivory, crucial for creating art and other specialised implements. End scrapers were used for preparing animal hides, essential for clothing and shelter. Projectile points became highly refined, including spearheads and eventually smaller, lighter points for arrows. The Solutrean laurel leaf points, for example, are exquisitely crafted, thin and symmetrical. Microliths were small, geometrically shaped stone inserts, often used as components in composite tools, such as barbs on harpoons or cutting edges on sickles. The manufacturing processes for these tools became increasingly sophisticated. Flint knapping, the art of shaping stone by controlled fracturing, involved various techniques. Percussion flaking involved striking a stone core with a hammerstone, a harder stone, or a soft hammer made of antler or wood to detach flakes. Soft hammer percussion allowed for more precise control and the production of thinner, broader flakes. Pressure flaking involved applying steady, localized pressure with a pointed tool made of bone, antler, or wood to detach small, precise flakes, allowing for fine-tuning of edges and creation of intricate shapes. In later periods, grinding and polishing techniques were also used, particularly for bone and antler tools to create smooth, durable surfaces for items like needles and harpoons. The function and use of these ancient tools were diverse and critical for daily survival. For hunting, tools evolved to improve efficiency and safety. Early thrusting spears with stone points required close proximity to dangerous prey. The invention of the atlatl, spear thrower, in the Upper Paleolithic dramatically increased the range and force of thrown spears, making hunting safer and more effective. Later, the development of the bow and arrow allowed for even greater distance and precision. Harpoons, made from bone or antler with barbed points, were crucial for fishing, For butchering and food preparation, sharp stone knives and choppers were used to dismember animal carcasses, strip meat, and break bones to access marrow. Grinding stones were used to process plant foods, grinding seeds or nuts into flour. Hide processing was essential for creating clothing and shelter. Scrapers were used to remove flesh and fat from hides, and awls, pointed bone tools, were used to pierce holes for stitching. Bone needles, with their fine eyes, allowed for the creation of tailored, multi-layered garments that provided vital insulation against the cold. Woodworking tools such as axes and adzes were used for shaping wooden shafts for spears, digging sticks, and possibly for constructing simple shelters. Burins were used to engrave and carve wood, bone, and antler into various implements and artistic objects. Tools were also used for creating art and ornaments. Engraving tools were used to create the intricate designs found in cave art and on portable objects. Drills were used to perforate shells or teeth for beads and pendants. The development of composite tools, where different materials were combined, represented a major technological leap. Hafting a sharp stone point onto a wooden spear shaft using sinew or plant fibres created a much more effective weapon than a simple sharpened stick. Similarly, attaching microliths to bone or wood to create barbed harpoons or serrated knives increased their cutting efficiency. This ability to combine materials demonstrated a complex understanding of material properties and engineering principles. The continuous refinement of ancient tools reflects the increasing cognitive abilities of Ice Age humans. Toolmaking required foresight, planning, and the ability to visualize a finished product from a raw material. It also involved teaching and learning, with knowledge and skills passed down through generations. The specialization of tools for specific tasks indicates a growing understanding of efficiency and problem solving. This technological progress allowed humans to expand their diets, adapt to new environments, increase their populations, and ultimately become the dominant species on the planet. The ancient tools found at archaeological sites are not just artifacts. They are tangible evidence of the intelligence, adaptability, and enduring spirit of our Ice Age ancestors. The mastery of fire was arguably the single most transformative technological innovation for early humans during the Ice Age, fundamentally reshaping their ability to survive and thrive in a challenging and often hostile world. While the exact timing of habitual fire use is debated, with evidence suggesting controlled fire use by Homo erectus as early as 1.5 million years ago, its widespread and consistent application became crucial for Homo sapiens and Neanderthals during the colder periods of the Pleistocene epoch. Fire provided a multifaceted advantage, offering warmth, protection, a means of cooking, and a tool for various crafts, all of which were essential for expanding human populations into new, colder territories. The ability to start and maintain fire was a complex skill. Early methods likely involved either percussion or friction. Percussion involved striking certain types of stone, such as flint, against iron-rich minerals like pyrite or marcasite to create sparks, which would then be caught on highly flammable tinder, like dry grass, moss, or fungus. Friction methods involved rapidly rubbing pieces of wood together, such as with a fire drill, spinning a stick into a divot on a baseboard, or a fire plough, rubbing a stick along a groove in a baseboard, to generate heat through friction until an ember formed. Once an ember was created, it would be carefully transferred to a tinder bundle and gently blown until it ignited into a flame. Maintaining fire was equally important, requiring a constant supply of fuel and protection from wind and moisture. This knowledge would have been passed down through generations, a vital part of cultural transmission. One of the most immediate and critical benefits of fire was warmth. During the long, harsh winters of the Ice Age, temperatures often plummeted far below freezing. Fire allowed humans to survive in otherwise uninhabitable cold environments, providing a central heat source in caves and temporary shelters. This ability to control their thermal environment was crucial for preventing hypothermia and frostbite, enabling humans to expand their geographical range into colder latitudes, such as northern Europe and Asia. Fire also extended the hours of activity beyond daylight, allowing for tool-making, social interaction, and other tasks to continue into the night. Fire also offered vital protection from predators. Large Ice Age carnivores, such as cave lions, bears, and wolves, were formidable threats. A roaring fire, with its light and heat, served as a powerful deterrent, keeping dangerous animals at bay from human encampments and shelters. This allowed humans to sleep more securely and reduced the constant threat of attack, particularly at night. The psychological comfort derived from the safety of fire would have been immense. Perhaps one of the most significant impacts of fire was on food preparation, specifically cooking. Cooking meat and plants made them more digestible, allowing humans to extract more nutrients from their food. This improved nutrition contributed to increased energy levels, better health, and potentially supported the development of larger brains. Cooking also reduced the risk of pathogens and toxins present in raw food, making the diet safer. Furthermore, cooking allowed humans to access a wider range of food sources that might have been indigestible or unpalatable when raw. Fire was also used for food preservation, such as smoking meat, which extended its shelf life and allowed for storage during periods of scarcity, a crucial strategy for surviving long winters. Beyond its direct benefits for survival, fire played a crucial role in toolmaking and modification. One key application was the heat treatment of stone. By carefully heating certain types of stone, such as flint or chert, early humans could alter their internal structure, making them easier to flake and allowing for the production of sharper, more predictable edges. This technique greatly improved the quality and efficiency of stone tools. Fire was also used to harden wooden spear tips. By charring the tip of a wooden spear in a fire, its hardness and durability could be significantly increased, making it a more effective weapon for hunting. Additionally, fire could be used to produce charcoal, which served as a black pigment for cave art and other symbolic expressions. Fire also had a profound impact on social cohesion and cultural development. The hearth became the central gathering point for early human groups. Around the warmth and light of the fire, individuals could share food, tell stories, transmit knowledge and skills to younger generations, and strengthen social bonds. It facilitated communication, planning, and the development of complex social structures. The communal aspect of fire likely contributed to the development of language and more intricate forms of social organization. It provided a focal point for rituals and ceremonies, embedding fire deeply within their cultural and spiritual lives. Furthermore, fire enabled humans to modify their living spaces. In caves, fires could be used to dry out damp areas, making them more habitable. Smoke from fires could also help to deter insects and other pests. The long-term use of fire in caves led to the accumulation of ash and charcoal layers, which are invaluable archaeological indicators of human occupation and activity. The controlled use of fire also had an impact on the broader landscape. While not on the scale of modern wildfires, early humans might have used fire to clear small areas of vegetation, creating open spaces that attracted game animals or promoted the growth of certain edible plants. The cognitive leap required for the consistent control and management of fire was substantial. It required an understanding of cause and effect, the properties of different materials, and the ability to plan and execute complex sequences of actions. The benefits derived from fire were so profound that it became an indispensable part of the human adaptive toolkit, allowing our ancestors to overcome many of the environmental limitations of the Ice Age. Its impact was far-reaching, influencing human diet, technology, social organization, and ultimately our species' ability to populate nearly every corner of the globe. The flickering flame of the hearth was not just a source of warmth, it was the crucible of human civilization. The harsh realities of the Ice Age compelled early humans to develop sophisticated strategies for shelter and clothing, essential elements for survival in a world dominated by extreme cold, strong winds, and frequent precipitation. Their ingenuity in harnessing available materials and mastering complex construction and fabrication techniques allowed them to extend their habitable zones into colder latitudes and endure the long, frigid winters. These adaptations were not static but evolved over hundreds of thousands of years, becoming increasingly refined during the late Pleistocene epoch. The most readily available and frequently utilized form of shelter was the natural cave or rock shelter. These geological formations offered immediate protection from the elements, including wind, rain, and snow, as well as providing a degree of thermal stability, as the interior temperature of a cave tends to fluctuate less than the outside air. Caves also offered inherent defense against large predators, providing a secure space for human groups. Archaeological evidence from numerous sites across Europe Asia and Africa shows continuous occupation of caves for thousands of years, with layers of ash, tools, and animal bones accumulating over time, reflecting generations of human habitation. Within these natural shelters, humans would often create distinct activity areas, such as hearths for fire, sleeping zones, and areas for tool-making or hide processing. They might have used simple windbreaks made of branches or animal hides near the entrance to further improve insulation and reduce drafts. The choice of a cave was strategic, often favouring those with south-facing entrances to maximise sunlight exposure and minimise cold winds, or those with specific internal structures that offered optimal protection. When natural caves were unavailable or unsuitable, Ice Age people constructed open-air shelters. The complexity of these structures varied greatly depending on the climate, available resources, and the duration of occupation. Early forms might have been simple brush huts or lean-tos, providing temporary respite. However, as the Ice Age intensified and humans moved into colder, treeless regions, more elaborate and durable structures became necessary. Perhaps the most remarkable examples are the mammoth bone huts found at numerous sites across the vast plains of Eastern Europe and Siberia, dating from around 25,000 to 15,000 years ago. These impressive dwellings demonstrate a sophisticated understanding of engineering and resourcefulness. The basic framework of these huts was constructed using the large, sturdy bones of woolly mammoths, an abundant resource in these regions. Mammoth skulls, mandibles, and pelvic bones were often used for the foundations, sometimes arranged in a circular or oval pattern. Long, curved mammoth tusks were frequently employed as structural supports for the roof, interlocking to form a dome or conical shape. The gaps between the bones would then be filled with smaller bones, branches, or earth to create a more solid wall. The entire structure was then covered with multiple layers of animal hides, likely from mammoths, reindeer, or other large animals, providing insulation and waterproofing. These hides would have been secured with ropes made from animal sinew or plant fibres. The interior of these huts would often feature multiple hearths for warmth and cooking, and evidence suggests they could house several families, indicating a communal living arrangement. Some sites show evidence of multiple huts forming small settlements, indicating a degree of permanence and social organisation. Beyond mammoth bones, other materials were used for open-air shelters. In areas with trees, wooden frameworks covered with hides or branches would have been common. In regions with abundant stone, simple stone foundations or low walls might have been built to support a hide or brush superstructure. The purpose of these shelters was not just protection from the elements, but also to create a secure base for hunting parties, a place to process game, and a safe environment for raising children. The ability to construct such shelters allowed humans to inhabit regions far from natural caves, expanding their territorial reach. Complementing shelter, clothing was an equally critical adaptation for surviving the Ice Age. Unlike earlier hominins who likely relied on natural body hair or minimal coverings, Homo sapiens and Neanderthals developed the ability to create tailored, multi-layered garments. This was a technological breakthrough that enabled them to maintain core body temperature in sub-zero conditions. The primary material for clothing was animal hides and furs. The skins of animals like reindeer, woolly mammoths, bison, Arctic fox, wolves, and various deer species were processed to create warm and durable garments. The process of creating clothing from raw hides was laborious and required specialised tools and skills. First, the hides had to be scraped clean of all flesh and fat using stone scrapers, often made from flint or chert. This step was crucial to prevent decay and make the hide pliable. Next, the hides needed to be softened to make them wearable. This could involve various methods such as chewing, pounding, or treating them with animal brains or fats. The softening process transformed stiff, raw hide into supple leather or fur. Once prepared, the hides would be cut into shapes using sharp stone knives. The ability to cut precise patterns was essential for creating tailored garments that fit the body closely, minimizing heat loss. The most significant innovation in Ice Age clothing technology was sewing. Archaeological discoveries of fine bone needles with eyes, some as small as a modern sewing needle, provide direct evidence of this skill. These needles, often made from bird bones or small mammal bones, allowed early humans to stitch together pieces of hide and fur with remarkable precision. The thread used for sewing would have been made from animal sinew, tendons, which is incredibly strong and durable, or from plant fibres. This ability to sew meant that clothing could be custom fitted, layered, and designed for maximum insulation. The types of garments worn by Ice Age people were likely similar in principle to those worn by modern indigenous peoples living in Arctic environments. They would have consisted of multiple layers to trap air and provide insulation. Basic garments would have included tunics or shirts, trousers or leggings, and hooded parkas or coats. The hood was particularly important for protecting the head and face from extreme cold and wind. Mittens or gloves and fur-lined boots were essential for protecting extremities from frostbite. The layering system allowed for adjustment to different activity levels and temperatures. For instance, a hunter might wear fewer layers during strenuous activity and add more when resting or in camp. The internal layers would have been made of softer, finer furs, while the outer layers might have been made of tougher, more water-resistant hides. The development of tailored clothing was not just about warmth. It also allowed for greater mobility and efficiency in hunting and foraging. Well-fitting garments would have enabled hunters to move quietly and effectively across the landscape without being hampered by bulky, ill-fitting attire. The ability to stay warm and dry for extended periods also increased the time humans could spend outdoors, expanding their foraging range and improving their chances of successful hunts. Hunting was a central and indispensable activity for Ice Age humans, providing not only the primary source of food, but also crucial raw materials for clothing, shelter, tools, and fuel. The vast landscapes of the Pleistocene epoch, teeming with large and often dangerous animals, demanded sophisticated hunting strategies, advanced weaponry, and a high degree of cooperation within human groups. The success of these hunting endeavours was paramount for survival, in a world where food resources could be scarce and unpredictable. The primary targets for Ice Age hunters were the abundant megafauna that roamed Eurasia and North America. These included iconic species such as woolly mammoths, woolly rhinoceroses, various species of bison like the steppe bison, wild horses, and different types of deer, including reindeer and the giant Irish elk. These large animals provided enormous quantities of meat, fat, and other vital resources. However, hunting such formidable creatures was inherently risky and required considerable skill, strength, and coordination. Beyond megafauna, humans also hunted a wide array of medium-sized game, such as smaller deer, wild boar, and various antelope species, and even smaller animals like Arctic foxes, hares, and birds, which provided supplementary food and valuable furs. The weapons used by Ice Age hunters evolved over hundreds of thousands of years, becoming increasingly effective and specialized. Early hunting tools were relatively simple, consisting mainly of thrusting spears with sharpened wooden tips or large, crudely flaked stone points. These weapons required hunters to get very close to their prey, engaging in dangerous direct confrontations. While effective for ambushing or dispatching already injured animals, they put hunters at significant risk. A major technological leap occurred with the invention of the atlatl or spear thrower during the Upper Paleolithic period. The atlatl is a simple lever device that effectively extends the length of a hunter's arm, allowing a spear or dart to be thrown with much greater force, speed, and accuracy over longer distances. This innovation dramatically increased the effective range of hunting, making it safer for hunters and more lethal for prey. It allowed hunters to strike large animals from a distance, reducing the risk of direct confrontation and enabling them to wound or kill prey before it could charge or escape. The atlatl transformed hunting into a more efficient and less dangerous activity. Later in the Ice Age, around 20,000 to 15,000 years ago, the bow and arrow emerged as another revolutionary hunting weapon. The bow and arrow provided even greater range, accuracy, and speed of projectile delivery than the atlatl. It allowed for rapid follow-up shots, and was particularly effective for hunting smaller, faster-moving game, as well as for delivering multiple hits on larger animals. The development of bows and arrows required sophisticated knowledge of materials, including resilient wood for the bow stave, strong sinew for the bowstring, and suitable stone or bone for the arrowheads. Beyond projectile weapons, hunters also used other tools and techniques. Traps and snares, made from plant fibers or animal sinew, would have been used to catch smaller animals. Harpoons, made from bone or antler with barbed points, were developed for fishing, particularly in coastal or riverine environments. Stone knives and scrapers were essential for butchering carcasses, skinning animals, and processing hides after a successful hunt. Hunting strategies employed by Ice Age humans were diverse and often highly sophisticated, reflecting a deep understanding of animal behaviour and the landscape. Ambush hunting was likely common, especially for solitary or smaller groups of animals. Hunters would hide near water sources, migration routes, or natural choke points and surprise their prey. Drive hunting involved groups of hunters working together to herd animals towards natural traps, such as cliffs, bogs, or narrow valleys, where they could be more easily killed. Archaeological evidence from sites like Solutré in France shows massive accumulations of horse bones at the base of a cliff, suggesting repeated drive hunts. This method required significant coordination and communication among hunters. Persistence hunting might have been employed for some species, where hunters would relentlessly track and pursue an animal until it collapsed from exhaustion. This strategy relies on human endurance and the ability to track prey over long distances. Cooperative hunting was crucial for taking down large megafauna. Groups of hunters would work together to surround, wound, and eventually kill animals like mammoths. This required careful planning, communication, and a division of labour, with some individuals driving, others attacking, and others ready to process the kill. The ability to cooperate on such a scale highlights the complex social organisation of Ice Age human groups. Hunters also had an intimate knowledge of animal migration routes and seasonal movements. They would position themselves along these routes to intercept herds, maximising their chances of a successful hunt. This required long-term observation and memory of animal behaviour patterns. The success of a hunt provided not only meat for immediate consumption, but also a wealth of other resources. Fat was particularly valuable in a cold environment, providing a dense source of energy and essential nutrients. Hides and furs were processed for clothing, blankets, and coverings for shelters. Bones were used for tools, weapons, and even structural components for huts. Antlers and ivory were carved into tools, weapons, and symbolic art. Sinews were used for thread and lashing. Every part of the animal was utilised, demonstrating a highly efficient and sustainable approach to resource management. Hunting was a dangerous undertaking. Even with advanced weapons, a wounded mammoth or bison could easily injure or kill a hunter. The risks were high, but the rewards were essential for survival. The evidence from archaeological sites, including vast bone beds, butchered remains, and specialised hunting tools, paints a clear picture of Ice Age humans as highly skilled, intelligent, and adaptable predators who mastered the art of hunting to thrive in a challenging world. Their success in this domain was a key factor in their ability to expand their populations and colonise diverse environments across the globe. The diet of Ice Age humans was a direct reflection of their environment, characterised by a heavy reliance on animal protein and fat, supplemented by a diverse range of plant foods, depending on regional availability and seasonal changes. Unlike modern diets, which are often based on agriculture and processed foods, the Ice Age diet was entirely composed of wild, naturally occurring resources, requiring constant foraging, hunting, and adaptation to ensure survival. The cornerstone of the Ice Age diet, particularly for human groups living in colder, high-latitude regions, was meat. Large animals, the megafauna of the Pleistocene, provided the most substantial source of protein and fat. Woolly mammoths, bison, reindeer, wild horses, and various species of deer were primary targets for hunters. The sheer size of these animals meant that a single successful hunt could provide food for an entire band for days or even weeks, depending on the size of the group and the ability to preserve meat. Every part of the animal was utilised: muscle meat for protein, organs for vitamins and minerals, and fat for energy. Fat was especially crucial in cold environments, providing a high-calorie energy source necessary to maintain body heat and fuel strenuous activities like hunting. Bone marrow, rich in fat and nutrients, was also highly prized and extracted by breaking open bones. The consumption of meat was not limited to large game. Medium-sized animals such as smaller deer, wild boar, and various antelope were also hunted regularly. Smaller animals, including Arctic foxes, hares, birds, and rodents, provided supplementary protein and fat, particularly when large game was scarce. Evidence from archaeological sites such as bone assemblages with cut marks and butchery patterns clearly indicates the systematic processing and consumption of a wide variety of animal species. The diet would have been rich in protein and healthy fats, providing the necessary energy for a highly active nomadic lifestyle. While meat formed a significant portion of the diet, especially in northern regions, plant foods were also an important component, though their archaeological preservation is less common. The availability of plants varied greatly depending on the specific environment and season. In warmer, more temperate regions, or during the warmer months in colder areas, a wider variety of plant resources would have been accessible. These included roots and tubers. These underground storage organs are rich in carbohydrates and can be found even when above-ground vegetation is scarce. Digging sticks, often made of wood, would have been used to extract them. Berries, seasonal fruits, rich in vitamins and antioxidants, would have been gathered when ripe. Nuts and seeds. These provide concentrated sources of fat, protein, and carbohydrates. Processing them might have involved cracking shells with stones or grinding seeds into flour using grinding stones. Leaves and shoots. Various edible greens would have been consumed, especially in spring and summer. Fungi. Certain mushrooms might have been part of the diet, though their seasonal nature and potential toxicity would have required careful identification. The importance of plant foods in the Ice Age diet is sometimes underestimated due to their poor preservation compared to bones and stone tools. However, analysis of dental calculus, hardened plaque on teeth, from Neanderthals and early Homo sapiens has revealed microscopic plant remains, including starch grains from grasses and tubers, confirming the consumption of a diverse range of plant matter. This indicates that even in colder climates, plant foraging was a consistent part of their subsistence strategy. Aquatic resources also played a role in the Ice Age diet, particularly for groups living near coasts, rivers, or lakes. Fish were caught using harpoons, nets, though evidence for nets is rare, or simple traps. Shellfish were gathered from coastal areas, providing an easily accessible source of protein and minerals. Birds and their eggs would have been collected seasonally. The exploitation of aquatic resources provided a reliable food source, especially when terrestrial game was scarce, and added dietary diversity. Food processing was crucial for making food safe, digestible, and palatable. The mastery of fire was paramount. Cooking meat over fire or on hot stones made it easier to chew and digest, increasing nutrient absorption and killing parasites. Cooking also allowed for the processing of certain plant foods that might be toxic or indigestible when raw. Drying and smoking meat were important preservation techniques, allowing for the storage of surplus food for leaner times, particularly during the long, unproductive winters. This ability to store food was a critical adaptation for nomadic groups, reducing their vulnerability to seasonal fluctuations in food availability. Grinding stones were used to process tough plant materials, turning seeds into flour for consumption. The Ice Age diet was highly adaptable to regional and seasonal variations. Human groups were opportunistic foragers, exploiting whatever resources were available in their specific environment at a given time of year. In the vast steppe tundra of northern Eurasia, meat from large herbivores would have dominated. In more temperate woodlands, a greater variety of plant foods and smaller game would have been available. Along coastlines, marine resources would have been central. This flexibility in diet was a key factor in the widespread success of Homo sapiens across diverse Ice Age landscapes. The nutritional implications of the Ice Age diet were significant for human development. The high intake of protein and fat provided ample energy for a physically demanding lifestyle. The diverse range of nutrients from both animal and plant sources supported brain growth and cognitive development. The challenges of acquiring food also drove the development of complex social behaviours, cooperative hunting strategies, and advanced tool technologies. The Ice Age diet was not just a means of survival, it was a powerful evolutionary force that shaped the physical and cognitive attributes of modern humans. During the Ice Age, the vast landscapes of Earth underwent dramatic shifts in climate and vegetation, compelling many animal species to engage in extensive migrations. These long-distance, often seasonal, movements were not merely journeys, but a fundamental survival strategy, allowing herds to access vital food resources, escape extreme cold, find suitable breeding grounds, and avoid predators. The ability to migrate was crucial for the persistence of many of the large mammals, known as Megafauna, that characterized the Pleistocene epoch. The primary driver for animal migration was the search for food and suitable pasture. The Ice Age was a time of fluctuating climates, with glacial periods bringing widespread cold and the expansion of tundra and steppe environments. While these treeless grasslands supported abundant vegetation, its availability could vary significantly with the seasons. During the long, harsh winters, snow cover could bury food plants, making them inaccessible. Animals like woolly mammoths, woolly rhinoceroses, bison, and wild horses, all large herbivores requiring vast quantities of forage, would undertake migrations to areas where food was still available or where snow cover was thinner. As spring arrived, they would follow the green-up of vegetation, moving to new pastures. For example, in North America, herds of bison and horses would have moved between summer grazing grounds in the northern plains and wintering grounds further south. Escape from extreme cold was another critical reason for migration. While many Ice Age animals possessed remarkable adaptations to cold, such as thick fur and a layer of fat, prolonged exposure to the most severe winter conditions could still be life-threatening, particularly for the young and old. Migrating to relatively warmer southern regions during winter months offered a reprieve from the biting winds and deep snows of the northern latitudes. This movement often involved crossing vast distances, sometimes thousands of kilometers, traversing diverse terrains including valleys, plateaus, and even emerging land bridges. The ability of a herd to collectively navigate these complex journeys was a testament to their inherent migratory instincts and learned behaviors passed down through generations. Finding suitable breeding grounds was also a key factor. Many migratory species synchronize their breeding cycles with periods of abundant food to ensure the survival of their young. After grueling journeys, herds would arrive at specific calving or birthing grounds, where ample fresh forage was available to support lactating mothers and rapidly growing offspring. These areas also often provided a degree of protection from predators. The concentrated birth of many young at once could also overwhelm predators, increasing the survival rate of the herd's newest members. Once the young were strong enough, the herd would resume its migratory journey. Avoiding predators was an ongoing challenge that influenced migration patterns. While large herds provided some defense through sheer numbers, predators like saber-toothed cats, cave lions, and wolves consistently followed their prey. By constantly moving, herds could avoid prolonged exposure to concentrated predator populations in any one area. The continuous movement meant that any individual predator or pack would have to expend significant energy to keep up, potentially reducing the overall pressure on the herd. Migrations could also take animals through less accessible terrain or across large bodies of water, further hindering predator pursuit. Some of the most prominent migratory species of the Ice Age include the reindeer, known as caribou in North America. Reindeer herds today undertake some of the longest terrestrial migrations on Earth, and their Ice Age ancestors likely did the same. These highly adapted deer would have moved between summer breeding and grazing grounds in the Arctic tundra and more sheltered wintering areas in boreal forests or slightly warmer grasslands. Their ability to dig through snow for lichen and moss made them uniquely suited to cold environments, but even they needed to follow the availability of their specialized forage. Woolly mammoths were also highly migratory animals. Their vast appetite for grasses and sedges meant they needed to constantly move across the steppe tundra to find sufficient forage. Evidence from isotope analysis of mammoth tusks, which grow incrementally like tree rings, shows chemical signatures that change with diet and environment, indicating long-distance seasonal movements. These migrations could have spanned hundreds or even thousands of kilometers, following the seasonal productivity of the vast grasslands they relied upon. Similarly, large herds of bison and wild horses would have undertaken extensive seasonal migrations across the plains of Eurasia and North America, driven by the search for fresh pastures and water. Their vast numbers would have visibly changed the landscape as they moved, consuming vast amounts of vegetation and trampling the ground. The mechanics of migration involved following established routes, often along river valleys, natural corridors or ancient paths that provided the easiest passage. Herd behavior was critical. Animals would move together in large groups, providing safety in numbers against predators. Older, experienced individuals, often matriarchs in the case of mammoths, would have led the herds, possessing the collective memory of successful routes and critical resources. Challenges during migration included river crossings, where animals could drown or be ambushed by predators, and navigating through difficult terrain such as mountain passes or areas with deep snow. The importance of migration for survival cannot be overstated. Without the ability to move across the landscape, many Ice Age megafauna would have been trapped in environments that became seasonally inhospitable, leading to starvation or excessive predation. Migration allowed them to exploit a wider range of resources throughout the year, ensuring a more consistent food supply. It also facilitated genetic exchange between geographically separated populations, maintaining genetic diversity and health within species. Furthermore, it allowed populations to escape disease outbreaks or localized environmental disturbances. The migratory patterns of Ice Age animals had a direct and profound impact on early human life. Human hunters, particularly Homo sapiens, often followed the large migratory herds, as these animals represented their primary food source and provided essential raw materials. This reliance on migratory game shaped human nomadic lifestyles, influencing where they established temporary camps, how they organized their hunts, and even their cultural practices. Archaeological sites are often found along ancient migration routes, indicating that humans strategically positioned themselves to intercept the moving herds. The knowledge of animal migration patterns was a crucial survival skill passed down through generations of human hunters. The influence of climate fluctuations on migration patterns was also significant, as glacial and interglacial cycles caused dramatic shifts in ice cover and vegetation. Animal migration routes would have changed over thousands of years. During periods of ice advance, migration routes would have been pushed southward. During warming periods, new areas would become accessible, allowing species to expand their ranges northward. The rapidity of some climate changes at the end of the Ice Age may have disrupted established migration routes, putting additional stress on populations already struggling with habitat changes and human hunting pressure, potentially contributing to the Megafauna extinction event. Thus, migration was not just a behaviour, but a dynamic response to a continually shifting global environment. Land bridges were crucial geographical features during the Ice Age, acting as temporary terrestrial corridors that connected continents or islands that are now separated by water. These vital links emerged as a direct consequence of the massive reduction in global sea levels during periods of extensive glaciation, allowing for the widespread dispersal of animals, plants, and crucially, early human populations into new territories. Their formation and eventual disappearance played a profound role in shaping global biodiversity and the distribution of species we see today. The mechanism of land bridge formation is inextricably linked to global sea level changes. During glacial periods of the Ice Age, vast amounts of the Earth's water became locked up in immense continental ice sheets and mountain glaciers. This process, where water evaporated from the oceans and precipitated as snow on land to form ice, effectively removed water from the global ocean basins. As a result, global sea levels dropped dramatically, exposing large areas of the continental shelf, the shallow underwater landmasses that extend from the edge of continents. Where these exposed shelves connected two previously separated landmasses, a land bridge was formed. When the ice sheets melted during interglacial periods, the water returned to the oceans, and sea levels rose, submerging these land bridges once again. These land bridges were not simply narrow strips of land. Some were vast, hundreds of kilometers wide, offering expansive plains and varied environments suitable for supporting diverse ecosystems. Their importance for species dispersal cannot be overstated. They acted as biological highways, allowing terrestrial animals and plants to migrate between continents and islands, facilitating genetic exchange and expanding the ranges of numerous species. This was a critical factor in the biogeographical history of many species, influencing evolutionary trajectories and creating patterns of distribution that are still studied today. The most famous and arguably most significant land bridge was Beringia, which connected northeastern Asia, Siberia, with northwestern North America, Alaska, across what is now the Bering Strait. During the last glacial maximum, when global sea levels were about 120 meters lower than today, Beringia emerged as a broad, unglaciated landmass, often hundreds of kilometers wide. Despite its high latitude, Beringia itself was largely ice-free because the air over it was too dry for significant snow accumulation. much of the available moisture was locked up in the massive ice sheets to the east and west. The climate of Beringia was characterized by a cold, dry grassland or steppe tundra environment, supporting a rich ecosystem. Beringia served as the primary route for the migration of numerous animal species between Asia and North America. Woolly mammoths, steppe bison, wild horses, reindeer, musk oxen, and various predators like wolves and saber-toothed cats all crossed Beringia in both directions, colonizing new continents. This bidirectional movement led to the exchange of fauna, influencing the evolution and distribution of many species on both continents. Crucially, Beringia also served as the gateway for the first human migrations into the Americas. Early Homo sapiens populations, who were highly skilled hunters and adapted to cold environments, crossed Beringia from Asia into Alaska, eventually spreading throughout North and South America. The exact timing and number of these human migrations across Beringia are subjects of ongoing scientific research, but it is clear that this land bridge was fundamental to the peopling of the Americas. Beringia was exposed multiple times during different glacial periods, indicating repeated opportunities for dispersal. Its final submersion occurred as sea levels rose around 11,000 years ago, severing the connection and isolating the populations that had crossed. Another well-known land bridge was Doggerland, which connected Great Britain to continental Europe across what is now the North Sea. During periods of lower sea level, this vast, low-lying landmass emerged, featuring river valleys, marshlands, and forests. Doggerland was a rich hunting ground for early human populations and supported various animal species, allowing for easy movement between the British Isles and the rest of Europe. Archaeological finds, including tools and animal bones, have been recovered from the submerged seabed, providing direct evidence of human presence on this now lost land. Doggerland was gradually submerged as sea levels rose at the end of the last glacial period, eventually forming the English Channel and separating Britain from the continent, a process that continues to influence its unique biodiversity. In Southeast Asia, the melting of ice sheets also created a large land bridge known as Sunderland. This landmass connected mainland Asia to the islands of Sumatra, Borneo, Java, and many smaller islands, forming a vast peninsula. Sunderland facilitated the widespread dispersal of Asian flora and fauna throughout Southeast Asia, leading to the rich biodiversity of the region today. It also played a critical role in the human migration into Australia and New Guinea. While this involved complex island hopping over water, the existence of Sunderland significantly reduced the oceanic distances that early mariners had to cross, making the journey much more feasible. Similarly, Sahul, the landmass connecting Australia and New Guinea, also emerged during glacial periods due to lower sea levels, further enabling dispersal within the Australasian region. The general impact of land bridges on biogeography and evolution was profound. They allowed species to expand their ranges into new continents, leading to increased competition, new predator-prey dynamics, and opportunities for speciation as populations became isolated again when the bridges submerged. They also facilitated the exchange of genetic material between previously separated populations, influencing the overall genetic diversity of species across continents. The periodic emergence and disappearance of these bridges created dynamic pathways for life, shaping the distribution patterns of plants and animals that scientists study today. The disappearance of land bridges, caused by the rising sea levels as the Ice Age ice sheets melted, was a gradual process over thousands of years but could also involve periods of relatively rapid inundation. As the climate warmed and glaciers receded, the vast quantities of water returned to the oceans, submerging these terrestrial connections. This resubmergence led to the isolation of populations, sometimes contributing to the evolution of unique island species, or in other cases to local extinctions if populations became too small or unable to adapt. The study of ancient land bridges provides crucial insights into past migration events, the causes of species distribution, and the dramatic impact of glacial cycles on Earth's geography and biodiversity. Global sea levels experienced profound and dramatic fluctuations throughout the Ice Age, directly driven by the waxing and waning of vast continental ice sheets and glaciers. These changes were not merely minor shifts, but represented colossal transfers of water between the Earth's oceans and its land masses, fundamentally altering coastlines, exposing new lands and influencing oceanographic processes. Understanding these eustatic sea level changes, which refer to global changes in the amount of water in the oceans, is central to comprehending the Ice Age environment. The primary mechanism behind these significant sea level changes was the glacial-interglacial cycle. During cold glacial periods, immense quantities of water evaporated from the Earth's oceans. Instead of returning to the oceans as rain, this precipitation fell as snow over continents and accumulated, compacting over millennia to form colossal ice sheets, some several kilometers thick, such as the Laurentide ice sheet in North America or the Scandinavian ice sheet in Europe. This process effectively locked up vast volumes of water on land, removing it from the global ocean system. As more and more water was stored as ice, the overall volume of water in the ocean basins decreased, causing global sea levels to drop significantly. Conversely, during warmer interglacial periods, like the one we are in today, these massive ice sheets and glaciers began to melt. The meltwater flowed back into the oceans, gradually increasing the volume of water in the ocean basins and causing global sea levels to rise. This cycle of falling and rising sea levels occurred repeatedly over the course of the Pleistocene Ice Age, with each major glacial maximum leading to a substantial drop in sea level. The scale of these sea level drops was immense. During the last glacial maximum, LGM, which peaked around 20,000 years ago, global sea levels were approximately 120 meters lower than they are at present. To put this into perspective, if all the ice sheets in Greenland and Antarctica were to melt today, global sea levels would rise by about 60 to 70 meters. The LGM drop was nearly double that, indicating the truly vast quantities of water that were locked away in continental ice. The most visible and immediate impact of these lowered sea levels was the exposure of vast areas of the continental shelf. Continental shelves are the gently sloping submerged edges of continents that extend outwards from the coastline. When sea levels dropped, these shallow underwater platforms became dry land. This exposed land dramatically altered the geography of the planet. What are now relatively shallow coastal waters became broad, flat plains. For instance, large parts of the North Sea, the Bering Strait, and the shallow seas of Southeast Asia became land. These newly exposed lands often supported unique ecosystems, ranging from cold tundra and grasslands in higher latitudes to more temperate or even drier environments in lower latitudes. They provided new habitats and migration routes for terrestrial animals and plants. The shape of coastlines was fundamentally different during glacial periods. Present-day bays, gulfs, and shallow seas often became dry land, or were greatly reduced in size. Islands that are now separated by water became connected to larger land masses or to each other, forming larger land masses or archipelagos. For example, the British Isles were connected to mainland Europe, and many of the islands of Southeast Asia were joined to the Asian mainland. Conversely, inland seas that are now large might have been much smaller or disappeared entirely. The dramatic shift in coastlines meant that the interface between land and sea was constantly moving, influencing coastal erosion, sedimentation, and the distribution of marine and terrestrial species. The formation and elimination of islands was a direct consequence of sea level changes. Many islands that are now isolated became peninsulas or were integrated into larger continental landmasses during glacial low stands. This allowed for the dispersal of terrestrial species that would otherwise be confined by oceanic barriers. When sea levels rose again, these land connections were severed, leading to the isolation of populations. This isolation could promote the evolution of unique island species through processes like island gigantism or dwarfism, or in some cases lead to local extinctions if the isolated populations were too small or unable to adapt to new conditions. Lowered sea levels also affected river courses. Rivers that currently flow into the sea would have extended their channels across the newly exposed continental shelves, sometimes cutting deep canyons into these areas. These extended river systems would have been critical pathways for meltwater drainage from retreating glaciers and for the movement of animals and humans across the broader landscapes. Beyond the visible impact on land, sea level changes also had profound effects on the ocean environment itself. The overall volume of the ocean basins was reduced, leading to changes in the shape and depth of marine habitats. While surface temperatures in high latitudes were colder, the deeper ocean waters might have seen shifts in their circulation patterns. The input of vast amounts of fresh water from melting glaciers during periods of deglaciation could have affected ocean salinity and density, potentially influencing global ocean currents, such as the Atlantic meridional overturning circulation, which plays a critical role in distributing heat around the planet. The expansion of glaciers also led to increased iceberg calving, introducing more fresh water and ice into the polar oceans. Scientists use various methods to study past sea level changes. Submerged archaeological sites and fossil evidence found on continental shelves provide direct proof of past lower sea levels and human activity on now submerged lands. Marine terraces, which are old, elevated shorelines now found above present-day sea level, indicate periods of higher sea level. Coral reef growth patterns also serve as excellent sea level indicators. Corals grow best in shallow, sunlit waters, so the depths at which fossil corals are found can tell us about past sea levels. Analysis of sediment cores from the ocean floor and coastal areas can also reveal changes in depositional environments linked to sea level fluctuations. The implications of these dramatic sea level changes for human migration and settlement patterns were immense. As discussed in the context of land bridges, exposed continental shelves provided new pathways for humans to colonize previously inaccessible continents. These newly exposed lands were often rich in resources, offering fertile hunting grounds and new areas for settlement. However, the subsequent rise in sea levels at the end of the Ice Age would have forced human populations to retreat from these coastal areas, inundating their settlements and changing their resource base. The rapid rates of sea level rise during some deglaciation periods, sometimes several centimeters per year, would have been a significant environmental challenge for coastal populations. The plant life of the Ice Age was profoundly shaped by the prevailing cold, dry, and often windy conditions, leading to distinct vegetation zones that differed markedly from many of today's landscapes. While the popular image of the Ice Age often focuses on massive ice sheets, the vast unglaciated areas and periglacial zones supported unique plant communities specifically adapted to the harsh climate. The distribution of these plant types was significantly shifted towards the equator compared to their modern ranges, and large dense forests were far less common in many regions that are now heavily wooded. The dominant vegetation type across much of the Northern Hemisphere's unglaciated lands during glacial periods was the mammoth steppe, or steppe tundra. This was a vast, treeless grassland ecosystem that stretched across Eurasia and Beringia, the land bridge connecting Asia and North America. It was characterized by a rich diversity of grasses, sedges, and herbaceous flowering plants, thriving in a cold, dry climate with seasonal moisture. Unlike modern tundra, which is often waterlogged and dominated by mosses and lichens, the mammoth steppe was more productive, supporting the immense herds of woolly mammoths, woolly rhinoceroses, bison, and horses that grazed upon its abundant forage. The productivity of this steppe tundra was crucial for sustaining the large megafauna populations. The plants in this environment were typically low-growing, with extensive root systems that could access water and nutrients in often shallow frozen soils. Their low stature also protected them from strong winds and prevented them from being completely buried by snow. Grasses were a fundamental component of the Ice Age flora. Various species of cold-tolerant grasses formed the base of the food chain for most large herbivores. These grasses were adapted to short-growing seasons and could withstand grazing pressure from vast herds. Sedges, grass-like plants that often grow in wet or marshy areas, were also prevalent, particularly in areas with seasonal meltwater or shallow permafrost. These plants provided important forage, especially during periods when other vegetation was less abundant. The presence of these highly nutritious grasses and sedges was key to the success of the large grazing animals. In colder, higher latitude areas, particularly closer to the ice sheet margins, tundra vegetation dominated. This ecosystem is characterized by low-growing plants that can survive in permafrost conditions and short, cool summers. Mosses and lichens were abundant, forming dense mats over the ground. While less nutritious than grasses for large grazers, they provided food for some specialized herbivores like reindeer and muskoxen. Dwarf shrubs, such as Arctic willows and dwarf birches, also grew in these areas, hugging the ground to avoid the worst of the wind and cold. These plants have shallow root systems because the ground beneath them remains permanently frozen. Their ability to photosynthesize at low temperatures and complete their life cycle rapidly during the brief summer was essential for their survival. Forests were significantly reduced in extent during glacial periods compared to today. The vast coniferous and deciduous forests that now cover much of Europe and North America were either absent or pushed much further south. Where forests did exist, they were often more open, with widely spaced trees, or confined to sheltered valleys and river corridors. Coniferous trees, such as spruce, pine, and larch, were more common in the colder northern forests that existed, as they are better adapted to cold temperatures and can retain their needles year-round, allowing for photosynthesis whenever conditions permit. Deciduous trees, which shed their leaves in winter, were generally restricted to more southern latitudes or warmer refugia, areas where populations survived during unfavourable conditions. The transition zones between tundra, steppe and forest were often characterised by boreal forest or taiga, a cold-tolerant coniferous forest. The distribution of plant species was directly influenced by the presence of permafrost. In areas with permanently frozen ground, only plants with shallow root systems could survive, as roots cannot penetrate the frozen layer. This limited the growth of large trees and favoured low-growing vegetation. The constant freezing and thawing of the active layer above the permafrost also created distinctive patterned ground, which influenced where certain plants could grow. The windy conditions of the Ice Age also played a role in shaping plant communities. Strong, persistent winds could cause desiccation, drying out, and physical damage to plants. Low-growing, cushion-forming plants were better able to withstand these conditions. The wind also played a crucial role in distributing loess, fine, wind-blown silt, which settled in thick layers over vast areas. While initially barren, these loess deposits, over time, could form fertile soils that supported the growth of grasses and other herbaceous plants, contributing to the productivity of the mammoth steppe. Pollen analysis, the study of fossilized pollen grains found in lake sediments, peat bogs, and ice cores, provides invaluable evidence for reconstructing Ice Age vegetation. Different plant species produce distinct pollen grains, and by identifying and counting these grains in successive layers of sediment, scientists can determine which plants were present in an area at different times in the past, and how vegetation changed over thousands of years. This method has shown clear shifts in plant communities corresponding to glacial and interglacial cycles, confirming the expansion of steppe and tundra during cold periods and the return of forests during warmer times. The plant communities of the Ice Age were not static. During the warmer interglacial periods within the larger Ice Age, such as the Eemian interglacial, around 125,000 years ago, forests would expand northward, and the climate would be more similar to today's. However, these periods were relatively short, and the dominant long-term trend during glacial phases was the prevalence of cold-adapted treeless biomes. The rapid warming at the end of the last glacial maximum, starting around 18,000 years ago, led to a dramatic and relatively swift transformation of plant landscapes. As ice sheets melted and temperatures rose, the steppe tundra began to give way to expanding forests and wetlands, fundamentally altering the habitats available for the megafauna and contributing to their eventual extinction. In summary, Ice Age plants were a testament to life's resilience in extreme conditions. The vast, productive mammoth steppe, dominated by cold-tolerant grasses and sedges, supported immense herds of megafauna. Tundra and dwarf shrubs characterized the coldest regions, while forests were largely confined to southern refugia or sheltered areas. These plant communities, shaped by temperature, wind, and permafrost, formed the ecological foundation of the Ice Age world, providing the sustenance for the remarkable animal life that defined the epoch. The river systems of the Ice Age were dynamic and profoundly altered by the presence and movement of vast continental ice sheets and mountain glaciers. The immense quantities of water locked up in ice, combined with the erosional and depositional power of the glaciers themselves, led to significant changes in river courses, flow regimes, and the formation of entirely new hydrological features. Rivers were not merely conduits for water, they were active participants in reshaping the landscape during glacial cycles. One of the most defining characteristics of Ice Age rivers, particularly those near the margins of melting ice sheets, was their nature as meltwater rivers. These rivers carried enormous volumes of water released from the melting ice. Unlike modern rivers, which are often fed by rainfall or stable snowmelt, glacial meltwater rivers experienced highly variable flows, with peak discharge often occurring during warmer summer months when ice melt was most intense. These rivers were typically braided, meaning they consisted of multiple interconnected channels weaving across a wide, shallow floodplain. This braided pattern was a result of the high sediment load carried by the meltwater. As the fast-flowing water lost energy, it would deposit large amounts of sand, gravel and silt, forcing the river to constantly shift its channels around these newly formed bars and islands. The immense sediment load in meltwater rivers originated directly from the glaciers. As glaciers moved, they scraped and ground away bedrock and picked up vast quantities of till, unsorted glacial sediment. When the ice melted, this sediment was released into the meltwater streams. These rivers deposited the coarser sediments, gravel and sand, in broad, flat areas known as glacial outwash plains or sanders, which extended for many kilometres beyond the ice front. Finer sediments like silt and clay were carried further downstream or deposited in proglacial lakes. The presence of advancing ice sheets often led to the diversion of existing river courses. As a glacier advanced, it could act as a massive dam, blocking the natural flow of a river. This forced the river to find new paths, often flowing along the ice margin or carving out entirely new valleys. For example, in North America, the southward advance of the Laurentide ice sheet repeatedly diverted the ancestral Missouri and Ohio rivers, forcing them into their present-day courses. The immense volumes of meltwater often created new, temporary drainage channels that flowed across the landscape. A significant feature associated with glacial rivers was the formation of proglacial lakes. These were large, often temporary lakes that formed at the margins of ice sheets, dammed by the ice itself or by glacial moraines. Meltwater would accumulate in these basins, sometimes forming lakes of truly colossal size. One of the most famous examples is Glacial Lake Agassiz in North America, which at its maximum extent was larger than all of the modern Great Lakes combined, covering vast areas of what is now Manitoba, Saskatchewan, Ontario, Minnesota and North Dakota. These proglacial lakes could exist for thousands of years, accumulating thick layers of fine sediments, varves, which provide valuable records of past climate and ice sheet dynamics. The sudden drainage of these proglacial lakes could lead to catastrophic floods, known as jökulhlaups, an Icelandic term for glacial outburst floods. When an ice dam failed, or a new outlet was carved, immense volumes of water would be released in a short period, creating torrents that scoured landscapes, carved massive channels, and deposited vast amounts of sediment over wide areas. The channeled scablands of Washington state, for instance, were formed by repeated jökulhlaups from Glacial Lake Missoula, which was dammed by an ice lobe in Montana. These floods were powerful geomorphological agents, dramatically reshaping entire regions in a matter of days or weeks. Beyond the direct influence of glaciers, rivers in unglaciated regions were also affected by the Ice Age climate. Changes in global atmospheric circulation and precipitation patterns led to altered rainfall regimes in many areas. In some regions that are now arid or semi-arid, increased rainfall during glacial periods led to the formation of large pluvial lakes and closed basins. These lakes, fed by increased runoff and reduced evaporation, indicate a wetter local climate than today. For example, in the Great Basin of the western United States, ancient Lake Bonneville, a much larger precursor to the Great Salt Lake, covered a vast area during the last glacial maximum. The rivers flowing into these pluvial lakes would have been more voluminous and persistent. Conversely, some regions that are now humid might have experienced drier conditions, leading to reduced river flow or even the drying up of some river systems. The lowering of global sea levels due to water locked in ice sheets also had a profound impact on rivers, particularly near coastlines. As sea levels dropped by as much as 120 metres, rivers extended their courses across the newly exposed continental shelves. This meant that river channels would have incised deeper into the exposed land, sometimes carving submarine canyons that are still visible today on the continental shelf. The base level of rivers, the lowest point to which they can erode, was significantly lowered, leading to increased erosion and downcutting in their lower reaches. When sea levels rose again at the end of the Ice Age, these extended river valleys were submerged, forming estuaries and bays. The presence of permafrost in periglacial zones also influenced river drainage, Since water could not easily infiltrate the permanently frozen ground, surface runoff was increased, leading to more widespread wetlands and shallow meandering rivers in summer. The thawing of the active layer above the permafrost could also lead to thermokarst features, such as uneven ground and small lakes, which influence local drainage patterns. The dynamic nature of Ice Age rivers meant that they were constantly reshaping the landscape. They transported and deposited enormous quantities of sediment, creating vast plains and deltas. They carved new valleys, diverted old ones, and created and drained immense lakes. The evidence of these ancient river systems, including their deposits, channels, and associated landforms, provides crucial insights into the hydrological processes and environmental changes that characterize the Ice Age world. Their legacy is still visible today in the landscapes shaped by their powerful flows. Volcanic activity, while not the primary driver of the Ice Age cycles, played a significant role in influencing Earth's climate during the Pleistocene epoch, sometimes contributing to cooling trends or causing short-term dramatic environmental shifts. The interaction between volcanoes and the vast ice sheets was a complex phenomenon, with eruptions potentially affecting ice dynamics and vice versa. Understanding this interplay requires distinguishing between the immediate short-term impacts of large eruptions and the long-term geological processes of volcanic carbon dioxide release. The most direct and immediate way volcanoes can impact climate is through the release of aerosols and ash into the atmosphere during large explosive eruptions. When a powerful volcanic eruption occurs, it can inject vast quantities of sulfur dioxide gas, along with fine ash particles, high into the stratosphere, the upper layer of the atmosphere. Once in the stratosphere, sulfur dioxide gas reacts with water vapour to form tiny sulfuric acid droplets, known as sulfate aerosols. These aerosols, along with the fine ash particles, can persist in the stratosphere for months or even years. Their presence creates a global veil that reflects incoming sunlight back into space before it can reach Earth's surface. This reflection leads to a measurable cooling effect on the planet's surface. The cooling from large volcanic eruptions can be significant, typically causing a global average temperature drop of a few tenths of a degree Celsius to a few degrees Celsius, lasting for 1 to 3 years. For example, the 1815 eruption of Mount Tambora in Indonesia caused the year without a summer in 1816, leading to widespread crop failures and famine in parts of Europe and North America due to unusually cold temperatures. During the Ice Age, a series of large, closely spaced volcanic eruptions could have contributed to a cumulative cooling effect, potentially pushing the climate towards colder conditions or intensifying existing glacial periods. While no single eruption would have caused an Ice Age, sustained periods of high volcanic activity, particularly from volcanoes located in high latitudes, could have exacerbated cooling trends initiated by other factors, such as Earth's orbital cycles. Evidence for past volcanic eruptions during the Ice Age comes from ice cores. Ice cores drilled from Greenland and Antarctic ice sheets contain layers of volcanic ash and elevated concentrations of sulfate, which can be precisely dated. These layers act as a historical record of past eruptions, allowing scientists to correlate volcanic events with climate changes recorded in the ice. For instance, studies of ice cores have identified numerous large eruptions during the Pleistocene, and some of these events coincide with periods of increased cooling or environmental stress. Beyond the cooling effect, volcanic ash itself can have localized impacts. If large amounts of ash fall on snow and ice surfaces, it can reduce the albedo, reflectivity of the ice. Darker ash absorbs more sunlight than pristine white snow, potentially leading to increased melting of glaciers and ice sheets in the immediate vicinity of the eruption. However, the global cooling effect from stratospheric aerosols typically outweighs this localized albedo effect on ice. The interaction between volcanoes and ice sheets was not always one-sided. Ice sheets themselves could influence volcanic activity. The immense weight of a thick ice sheet can suppress volcanic eruptions by increasing the pressure on magma chambers beneath the surface. When ice sheets melt and retreat, this pressure is removed, a process called decompression. This decompression can lead to an increase in volcanic activity, as the underlying magma is able to rise more easily to the surface. This phenomenon has been observed in places like Iceland, where volcanic activity increased following the retreat of glaciers at the end of the last ice age. Therefore, as glaciers melted during interglacial periods, they might have inadvertently triggered more eruptions, which could then, in turn, have a temporary cooling effect. Subglacial eruptions, where volcanoes erupt beneath ice sheets, are also a unique interaction. These eruptions can melt vast quantities of ice, creating enormous subglacial lakes. If the water in these lakes is suddenly released, it can cause catastrophic floods known as Glacial. These floods can carry immense amounts of sediment and reshape landscapes, as seen in Iceland. While not a direct climate driver, these events demonstrate the dynamic and sometimes violent interplay between volcanic heat and glacial ice. On much longer geological timescales, volcanic activity also plays a critical role in Earth's climate by releasing carbon dioxide, CO2, into the atmosphere. CO2 is a powerful greenhouse gas, and over millions of years, volcanic emissions are a primary natural source of atmospheric carbon. However, the rate of CO2 release from volcanoes is typically very slow and steady. While sustained periods of very high volcanic activity over millions of years could contribute to long-term warming trends, the relatively short-term glacial-interglacial cycles of the Ice Age, tens of thousands to hundreds of thousands of years, are driven by factors like Earth's orbital cycles, not by fluctuations in volcanic CO2 emissions. The cooling effect from volcanic aerosols is a much more immediate and short-lived phenomenon compared to the long-term warming effect of CO2.